Hello. Welcome to this peaceful space where we're going to explore together one of the most fascinating questions of human existence: time. Don't worry about paying attention to every single word. Just relax, breathe gently, and let these ideas flow through your mind like a calm river. Time is always with us, from the moment we wake up until the instant we fall asleep. Time accompanies us silently. We look at the clock. We count the minutes, we wait for days to pass or wish that special moments would last forever. But if we stop to think calmly, we'll notice something curious. What exactly is time? This simple question has intrigued philosophers, scientists, and ordinary people for thousands of years. And the answer isn't as simple as it seems. Time isn't something we can touch, like we touch a stone. It isn't something we can see, like we see a tree. Time is different. It's more like an invisible dimension that permeates everything around us. Imagine for a moment that you're sitting in a tranquil garden. The flowers sway gently in the breeze. The clouds move slowly across the sky. You notice that the shadows change position as the sun travels across the sky. All these changes happen in time, but where is time? You cannot point to it. You cannot hold it, and yet you know it's there, flowing constantly. Human beings have always tried to understand time through what they can observe. Our ancestors looked at the sky and saw the sun rise and set. They saw the moon change shape, waxing and waning. They observed the seasons alternating, spring arriving with its flowers, summer with its warmth, autumn with its falling leaves, and winter with its cold. All these natural cycles gave people a sense of time passing, but time itself remained a mystery. It was as if there were an invisible current carrying everything forward, and we, like leaves in a river, simply followed along. When you think about your own life, you realize that it's all organized around time. Your memories are events that happened in the past. Your plans are things you hope to do in the future. And this moment right now, as you listen to these words, is the present: past, present, and future. Three simple words that describe our experience of time. But here's something interesting to consider calmly. The past has already happened. It no longer exists except in our memories. The future hasn't arrived yet. It exists only as possibility, as something we imagine. And the present? Well, the present is so brief that by the time we try to define it, it has already become the past. So in a certain sense, the only time that truly exists is this fleeting instant we call now. And even this now is difficult to capture. It's like trying to hold water in your hands. It slips between your fingers, no matter how hard we try to hold it. Ancient philosophers already reflected on this. St. Augustine, a thinker from the 4th century, wrote something very beautiful about time. He said, "What then is time? If no one asks me, I know. If I want to explain it to someone who asks, I no longer know." This phrase perfectly captures the enigma of time. We all have an intimate sense of what time is. We know when we're bored and time seems to pass slowly. We know when we're having fun and time seems to fly. But explaining exactly what time is, that's much more difficult. Let's think about this in another way, very calmly. Imagine you're watching a movie. The movie tells a story that unfolds from beginning to end. There's a clear sequence of events. First one thing happens, then another, and then another. This sequence is temporal. The events in the movie are organized in time. Now here's something to consider gently. The entire movie already exists. If it's recorded on a disc or stored in a file, all the scenes are already there, complete. The beginning, the middle, and the end all exist simultaneously in that storage. But when you watch the movie, you experience it sequentially, moment by moment. You cannot skip to the end without missing the middle. You experience the movie in time, even though the movie itself exists all at once. Could the universe be similar? Could all moments, past, present, and future, exist simultaneously, like scenes in a movie, even though we experience them one at a time? This is one of the deep questions we'll explore gently throughout our time together. Time also has a direction. We call this the arrow of time. Things seem to move in one direction, forward. We age, we don't grow younger. A cup falls and shatters, but shattered pieces don't spontaneously reassemble into a cup. Waves wash footprints away from the beach, but the waves don't create footprints. There's a natural flow from order to disorder, from past to future. Why is this? Why can't time go backward? These are questions that have puzzled thinkers for centuries, and we'll explore them calmly as we continue. For now, just rest in this thought. Time is mysterious. It's something we all experience, yet something we struggle to define. It's invisible, yet it shapes everything we do. It cannot be stopped, yet it sometimes seems to slow down or speed up depending on our experiences. The beauty of this mystery is that it invites us to wonder, and wondering, done calmly and without urgency, is one of the most peaceful activities we can engage in. There's no rush to understand everything immediately. We have time, plenty of time, and we'll use it gently to explore these fascinating ideas together. Think about how different cultures have understood time. Some cultures view time as circular, like the seasons that repeat endlessly. Spring follows winter, which follows autumn, which follows summer, which leads back to spring again. Birth, growth, death, and rebirth. The cycle continues forever. Other cultures view time as linear, like an arrow shot from a bow. It begins at one point and travels forward to another point, never returning. History unfolds in a straight line, from creation to an eventual end. Both views capture something true about our experience. Nature does seem cyclical. Days repeat, seasons return. Yet our lives seem linear. We are born, we live, and we die. We don't live the same day over and over, even if days can feel similar. Perhaps time is both, cyclical in some ways, linear in others. Perhaps it's more complex than our simple categories can capture. And that's perfectly fine. We don't need to have all the answers right away. We can simply observe, consider, and appreciate the mystery. As you rest here listening to these words, you are existing in time. Seconds are passing. Minutes are accumulating. The Earth is rotating on its axis, carrying you through space. The Earth is orbiting the Sun. The Sun is moving through the galaxy. The galaxy itself is moving through space. All of this is happening simultaneously. All of it is temporal. All of it is occurring in time. And yet, from your perspective, you might simply be lying comfortably, breathing steadily, listening to a voice discussing abstract ideas. The grand cosmic dance and your simple moment of rest are both real, both happening in time, both equally valid ways of experiencing this mysterious dimension we call time. Let's consider another aspect gently. Time seems to be connected to change. If nothing ever changed, would time exist? Imagine a universe where everything was perfectly still. Every atom frozen in place. No movement, no change, no processes unfolding. Would time still pass in such a universe? This is a question philosophers have debated. Some say that time requires change. Without change, the concept of before and after becomes meaningless. If everything is always the same, there's no way to distinguish one moment from another. Others suggest that time could exist even without change. Time, they argue, is a fundamental feature of reality, a stage on which events occur. Even if no events are occurring, the stage remains. We don't need to decide who is right. We can simply appreciate both perspectives, understanding that each captures something important about how we think about time. What we do know from our direct experience is that our world is full of change. Leaves fall from trees, water flows in streams, clouds drift across the sky. Our hearts beat steadily, our lungs expand and contract with each breath. All of this is change, and all of this happens in time. The ancient Greek philosopher Heraclitus said, "You cannot step into the same river twice." What he meant is that a river is constantly flowing. The water you step into one moment has flowed away by the next moment. The river is always changing, even though we call it by the same name. In the same way, you are constantly changing. The cells in your body are being replaced. Your thoughts are flowing like a stream, The person you were yesterday is slightly different from the person you are today, even if the changes are so gradual you don't notice them. This is both beautiful and slightly melancholic. Nothing lasts forever. Everything is temporary. And yet, this very impermanence gives meaning to our experiences. If moments lasted forever, they wouldn't be special. It's precisely because time passes that we cherish beautiful moments, that we value our experiences, that we appreciate the people in our lives. So time, in this sense, is a gift. It allows for change, for growth, for new experiences. Without time, everything would be frozen, static, unchanging. With time, life becomes possible. Stories can unfold. Learning can happen. Love can grow. As we continue our exploration, we'll look at time from many different angles. We'll consider what physics tells us about time. We'll explore how we perceive time psychologically. We'll think about time's relationship to space. We'll contemplate the beginning and possible end of time. We'll wonder about the nature of now. But we'll do all of this gently, without hurry, letting each idea settle softly into your awareness before moving to the next. There's no test at the end, no pressure to remember everything. This is simply an invitation to wonder, to consider, to let your mind explore these fascinating questions in a relaxed and peaceful way. Time is a mystery we live inside. We are temporal beings, creatures who exist in time, whose lives are shaped by time, who experience the flow of moments from past to future. And yet, time itself remains elusive, difficult to grasp, resistant to simple definitions. Perhaps that's how it should be. Perhaps some mysteries are meant to be lived rather than solved. We can understand aspects of time, we can measure it and study it, but the full nature of time may always retain an element of wonder. And wonder, as we've said, is a beautiful state to be in. It opens us up. It makes us curious. It reminds us that despite everything we know, there's always more to learn, more to discover, more to appreciate. So let's continue this gentle exploration together, allowing time itself to guide us through these ideas, moving at its own steady pace, unhurried and calm. Before we can understand what time truly is, it helps to consider how we measure it. Measuring time is something humans have done for thousands of years, and the methods we've developed tell us a lot about how we think about time itself. Look around you right now, wherever you are. Somewhere nearby there's probably a clock. Maybe it's on your wall, maybe on your wrist, maybe on your phone. Clocks are everywhere in modern life. We rely on them constantly. We schedule our days around them. We coordinate with other people using them. But clocks are a relatively recent invention in the grand span of human history. Long before clocks existed, people still needed to measure time. They needed to know when to plant crops, when to harvest, when to prepare for winter. They needed to coordinate activities with others in their community, so they looked to nature for guidance. The most obvious natural clock was the sun. Every day the sun rose in the east and set in the west. This cycle was reliable, predictable and visible to everyone. A day became a natural unit of time. People could divide their activities according to the sun's position in the sky. Morning tasks, midday tasks, evening tasks. This simple system worked well for basic timekeeping, but the day could be divided further. People noticed that shadows changed length and direction as the sun moved across the sky. By placing a stick in the ground and watching its shadow, they created the first sundials. These devices could divide the day into smaller portions, giving people a more precise way to track time's passage. At night, when the sun was gone, people looked to the stars. The stars moved across the sky in predictable patterns. Certain stars would rise at certain times of year. The position of constellations could tell you what season you were in, how much of the night had passed. The night sky became a vast clock for those who knew how to read it. The moon provided another natural measure. Its phases followed a regular cycle from new moon to full moon and back again. This cycle took about 29.5 days. Many cultures based their calendars on the lunar cycle. A month was originally the time between one new moon and the next. Seasons gave an even longer measure of time. The ancient Egyptians noticed that the Nile River flooded at regular intervals. They observed that certain stars appeared in the sky just before the flood came. By tracking these astronomical events, they could predict the seasons and plan their agriculture accordingly. All of these natural cycles, days, months, seasons, years, gave humanity its first clocks. These clocks were built into the cosmos itself. The Earth's rotation created day and night. The Moon's orbit created months. The Earth's orbit around the Sun created years and seasons. Time was something you read from the sky. But these natural clocks had limitations. What if you needed to measure shorter periods of time? What if you needed to know how much time had passed when the sun wasn't visible, or when you were indoors? People got creative. They invented devices that could measure time independently of the sun and stars. One of the earliest was the water clock, also called a clepsydra. The principle was simple. Water dripped from one container into another at a steady rate. By marking levels on the receiving container, you could see how much time had passed based on how much water had accumulated. Water clocks were used in ancient Egypt, Greece, China, and many other civilizations. They had advantages over sundials. They worked at night indoors on cloudy days. But they had their own problems. The flow rate of water could change with temperature. The containers needed regular refilling. Still, for centuries, they were among the best timekeeping devices available. Another ancient timing device was the hourglass, which used falling sand instead of dripping water. You've probably seen one before. Two glass bulbs connected by a narrow neck, with sand flowing from the upper bulb to the lower one. When all the sand had fallen, a set amount of time had passed. Hourglasses were particularly useful at sea, where the motion of a ship would make water clocks unreliable. Candles could also measure time. A candle marked with lines would burn down at a predictable rate. By seeing which mark the flame had reached, you could estimate how much time had passed. Incense sticks worked similarly in some Asian cultures. These methods weren't precise, but they were simple and accessible. All of these early timekeeping devices shared something in common. They measured time by measuring change. Water dripping, sand falling, candles burning, shadows moving. Time was understood as something that could be tracked by observing processes that unfolded steadily and predictably. The real revolution in timekeeping came with mechanical clocks. These devices used gears, weights, and eventually springs to create regular repeating motion. The first mechanical clocks appeared in medieval Europe around the 13th century. They were large, expensive, and not very accurate, but they represented a new way of thinking about time. A mechanical clock doesn't depend on any natural cycle. It creates its own regular rhythm through mechanical means. A weight pulls on gears, or a spring unwinds, driving hands around a dial. The clock ticks away, second after second, minute after minute, independent of the sun, the moon, or the stars. Early mechanical clocks were often installed in church towers, where their bells would ring out the hours. This public timekeeping was important. It allowed communities to coordinate their activities more precisely. Markets could open at set times. Workers could know when to start and end their shifts. Time was becoming more structured, more regulated. But these early clocks were still quite inaccurate. They might gain or lose 15 minutes in a day. For many purposes, this was good enough, but as science and navigation advanced, people needed more precise timekeeping. The breakthrough came with the invention of the pendulum clock in the 17th century. The physicist Christian Huygens realized that a pendulum swings back and forth at a very regular rate. This rate depends on the length of the pendulum and the strength of gravity, but it doesn't change much regardless of how wide the swing is. This property, called isochronism, made pendulums perfect for regulating clocks. Pendulum clocks were far more accurate than anything that came before. They could keep time to within seconds per day. This level of precision opened up new possibilities in science and navigation. Astronomers could make more accurate observations. Ships could determine their longitude more reliably. As clockmaking advanced, clocks became smaller and more portable. Pocket watches became status symbols among the wealthy. By the 20th century, wristwatches were common. Time had become personal. Everyone could carry their own clock, synchronized with everyone else's. But even the best mechanical clocks weren't perfect. Temperature changes could affect the length of the pendulum or the tension of springs. Friction would gradually slow the mechanism. Clockmakers developed ingenious solutions to these problems, but mechanical limitations remained. The next revolution came with electronic and atomic clocks. In the 20th century, scientists discovered that certain crystals, like quartz, vibrate at extremely regular frequencies when electricity passes through them. A quartz watch uses these vibrations to keep time. Quartz clocks are accurate to within seconds per year, far better than even the finest mechanical timepieces. But scientists wanted even more precision. They turned to atoms themselves. Certain atoms, like cesium, absorb and emit electromagnetic radiation at extremely precise frequencies. These frequencies don't change. They're the same for every cesium atom in the universe. By using these atomic oscillations as a reference, scientists created atomic clocks. Atomic clocks are astonishingly accurate. The best atomic clocks in existence today wouldn't gain or lose even 1 second in hundreds of millions of years. They're so precise that they've revealed something interesting. Earth's rotation isn't perfectly regular. Days are very slightly different lengths. Atomic clocks are more regular than the planet itself. This incredible precision has practical applications. GPS satellites, for example, rely on atomic clocks. Your phone can determine your location by comparing time signals from multiple satellites. Even tiny errors in these clocks would cause large errors in position. The modern world runs on precise timekeeping. But let's step back from the technology for a moment and consider what all of this means. We've gone from reading time from the sun's position to measuring it with devices that count oscillations of atoms. We've gone from dividing the day into rough periods to measuring billionths of a second. Why have we done this? Why has humanity invested so much effort into measuring time more and more precisely? Part of the answer is practical. Navigation requires accurate clocks. Science requires precise measurements. Modern technology requires synchronization. But there's something deeper here too. By measuring time, we're trying to understand it. We're trying to grasp something invisible and make it tangible. Every clock, from a sundial to an atomic clock, is essentially doing the same thing. It's counting regular events. The sun crosses the sky once per day. A pendulum swings back and forth at a regular rate. A cesium atom oscillates at a specific frequency. By counting these events, we measure time. But notice what we're actually doing. We're not measuring time directly. We're measuring change and using that to infer how much time has passed. We assume that certain processes, pendulum swings, atomic oscillations, happen at constant rates. We define time intervals based on how many of these events occur. In fact, our modern definition of the second is based on cesium atoms. 1 second is defined as the duration of exactly 9,992,631,770 oscillations of a cesium-133 atom. This isn't arbitrary. This number was chosen so that the new definition would match the old definition based on Earth's rotation, but it represents a fundamental shift in thinking. We've moved from defining time based on astronomical cycles to defining it based on atomic physics. We've taken timekeeping from the cosmic scale to the quantum scale, and in doing so, we've achieved unprecedented precision. Yet with all this precision, with all our sophisticated clocks and our exact measurements, we still haven't answered the fundamental question: what is time? We've gotten very good at measuring it, but measuring something and understanding its true nature are different things. It's like measuring the temperature without understanding what heat really is. For a long time, people could measure temperature with thermometers, but they didn't know that heat was molecular motion. The thermometer measured something real, but the underlying nature of that something remained mysterious. Similarly, our clocks measure something real. Time is real. It passes. Events happen in sequence. Causes precede effects. But what time actually is, what gives it its properties, why it flows in one direction, these questions aren't answered by building better clocks. Still, precise timekeeping has revealed important truths about time. For example, atomic clocks have confirmed predictions from Einstein's theory of relativity. Time doesn't pass at the same rate everywhere. Time runs slightly slower in strong gravitational fields. Time runs slightly faster for objects in motion. These effects are tiny, but atomic clocks can detect them. Two atomic clocks, one on the ground and one in an airplane, will show slightly different times after a flight. The difference is only nanoseconds, but it's real and measurable. Time itself is flexible, variable, relative. This is a profound discovery, one that would have been impossible without precise timekeeping. We'll explore these ideas more deeply in later chapters. For now, just appreciate how far humanity has come in measuring time. From watching shadows to counting atomic oscillations, we've developed increasingly sophisticated tools to track time's passage. And yet, in our daily lives, we still experience time much as our ancestors did. We wake with the sun. We feel hungry at mealtimes. We grow tired at night. Our bodies have internal clocks, biological rhythms that pulse with their own regular beats. We might check atomic clocks for the precise time, but we feel time in a more ancient, intuitive way. This is part of time's mystery. It's both objective and subjective, both measurable and felt, both cosmic and personal. We can count its passage with extraordinary precision, yet we experience it differently depending on our circumstances. Time is both a dimension we measure and an experience we live. As you rest here listening to these words, time is passing, clocks are ticking, atoms are oscillating, the earth is turning, and you are experiencing this moment, this present, this now. The clocks can tell you exactly what time it is, down to the nanosecond. But only you can know what this time feels like, what it means to you, how you're experiencing it. That's the beautiful paradox of time. It's universal. The same time applies to everyone, yet it's deeply personal. We all share time, yet we each experience it uniquely. Now that we've explored how we measure time, let's turn our attention to how we experience it. Because there's something fascinating about time perception. It's not constant. Sometimes time seems to crawl by slowly. Other times it flies past in what feels like an instant. The clocks tick at their steady, regular pace, but our experience of time is fluid and changeable. Think back to your childhood. Remember how long summer vacations felt. Those endless days of freedom, playing outside, exploring, discovering. A single summer could feel like a lifetime. 3 months stretched out before you, like a vast ocean of time. You could do so much, experience so much, and still the summer wouldn't be over. Now think about recent summers as an adult. They seem to pass in a blink. One moment it's June, and suddenly it's September. Where did the time go? The same 3 months that felt eternal in childhood now feel fleeting and brief. This isn't your imagination. This is a real phenomenon that many people experience. As we age, time seems to accelerate. Years that felt long in childhood feel short in adulthood. This raises a fascinating question. Why does our perception of time change? Scientists and psychologists have proposed several explanations. One theory suggests it has to do with novelty and attention. When you're a child, everything is new. You're constantly learning, constantly encountering things you've never seen before. Your brain is highly engaged, processing a flood of new information. This creates rich, detailed memories. When you're an adult, much of life becomes routine. You've driven to work 1,000 times. You've cooked dinner countless times. You've had similar conversations, watched similar shows, followed similar patterns. Your brain doesn't need to pay as much attention because it already knows what to expect. This creates less detailed memories. Here's where it gets interesting. We seem to judge time's passage partly based on memory. When you look back on a period of your life, if you have many rich, detailed memories, that period feels like it lasted a long time. If you have few memories, sparse and vague, that period feels like it passed quickly. Children form dense, detailed memories because everything is new and engaging. Adults, living more routine lives, form fewer distinctive memories. So when a child looks back on summer, they remember many specific moments, many adventures, many discoveries. When an adult looks back, the days blur together, indistinct and similar. This suggests something profound. Time might feel longer when we're paying attention. When we're fully present, fully engaged, experiencing each moment consciously, we create richer memories. And those richer memories make time feel more substantial, more real, longer. There's another factor too: proportion. When you're 5 years old, 1 year represents 20% of your entire life. It's a huge portion of everything you've experienced. When you're 50 years old, 1 year is only 2% of your life. Proportionally, it's much smaller. Some researchers think this proportional effect influences how long time feels. Each year becomes a smaller fraction of your total life experience, so it feels shorter in comparison. This is sometimes called the proportional theory of time perception. But time perception varies not just across our lifespan, but from moment to moment. You've surely experienced this. When you're bored, waiting for something, time drags. 5 minutes can feel like an hour. You check the clock, convinced significant time has passed, only to discover it's been 2 minutes. On the other hand, when you're deeply absorbed in something enjoyable, reading a good book, having a great conversation, playing a game, time vanishes. Hours can pass in what feels like minutes. You look up, startled to discover how much time has gone by. Why does this happen? It seems to relate to attention and consciousness. When you're bored, you're very aware of time passing. You're thinking about time, watching it, waiting for it to move. This focused attention on time itself makes you acutely conscious of each moment, stretching out your experience. When you're engaged and enjoying something, you're not thinking about time at all. Your attention is completely absorbed in the activity. You're not watching the clock, you're not counting the minutes. Time becomes invisible, and paradoxically, this makes it seem to pass quickly. There's a phrase for this state of complete absorption: flow. Psychologist Mihaly Csikszentmihalyi studied this phenomenon extensively. Flow is when you're so involved in an activity that everything else fades away. You lose track of time, lose self-consciousness, become one with what you're doing. Athletes call it being in the zone. Artists talk about losing themselves in their work. During flow states, time seems to disappear. This is one of the characteristics that makes flow so enjoyable. You're not worried about the past or future. You're completely in the present moment. And in that state, clock time becomes irrelevant. Subjective time takes over. Emotions also affect our time perception. Fear and anxiety tend to slow time down. If you've ever been in a dangerous situation, a car accident, a fall, a moment of genuine terror, you might remember it as happening in slow motion. People often report that time seemed to stretch out during frightening experiences. This makes evolutionary sense. When you're in danger, your brain shifts into high alert. It processes information faster, pays more attention to details, prepares your body for action. This heightened state of awareness creates more detailed memories, which makes the experience feel longer when you recall it. Researchers have tested this in various ways. In one famous experiment, people were dropped from a tall platform into a safety net. It was scary but safe. Participants consistently overestimated how long they were falling. They thought it took longer than it actually did. Their brains, in high alert mode, made time feel stretched out. Positive emotions can also affect time perception, though differently. When we're happy and enjoying ourselves, time often feels like it's passing quickly in the moment. But when we look back on happy times, we often remember them as lasting longer than unhappy times. This might be because happy experiences are more vivid and memorable. Sadness and depression can make time feel heavy and slow. People experiencing depression often report that time drags, that days feel endless and empty. This might relate to the lack of engagement and pleasure that characterizes depression. Without positive experiences to mark time, Moments blur together into a grey sameness. Our age affects not just how long periods of time feel, but how we think about time. Young children have limited concept of future time. They live mostly in the present. A young child can't really imagine next week or next month. Their time horizon is short. As we mature, our sense of time extends. We learn to plan ahead, to delay gratification, to think about long-term consequences. Teenagers can think months or years into the future, though the distant future still feels abstract. Adults can contemplate decades ahead, planning for retirement, thinking about their children's futures. Interestingly, as people get very old, their time perspective often shifts again. The future becomes shorter, there's less of it ahead. The past becomes more prominent. Elderly people often spend more time reminiscing, revisiting memories, reflecting on their lives. Their temporal focus shifts from future to past. Culture also shapes how we perceive and think about time. Western industrial cultures tend to view time as linear and valuable. Time is money. Time is something to be managed, scheduled, optimized. People in these cultures often feel rushed, pressured by time's passage. Other cultures have different relationships with time. Some indigenous cultures have more cyclical views, where time repeats in patterns. Some cultures are more present-focused, less concerned with punctuality and schedules. The way you think about time is partly cultural, learned from the society you grow up in. Language even affects time perception. Different languages express time differently. Some languages have elaborate tense systems, making fine distinctions between different times. Other languages have simpler tense systems. Some research suggests that the way your language handles time might subtly influence how you think about it. Let's consider another curious aspect of time perception: the difference between prospective and retrospective timing. Prospective timing is how long something feels while you're experiencing it. Retrospective timing is how long it feels when you look back on it later. These can be quite different. A boring meeting might feel endless while you're sitting through it. Prospective time drags, but later, when you try to remember the meeting, you might have trouble recalling specific details. Retrospectively, it might seem like it passed quickly because you have few memories of it. Conversely, an exciting vacation might fly by while you're experiencing it. Prospective time seems short, but when you return home and look through your photos, remembering all the things you did and saw, it might feel like you were gone for much longer. Retrospectively, the time feels extended because of your rich memories. This distinction helps explain the paradox of aging. As you get older, prospective time might feel faster. Days and weeks seem to rush by. But when you look back on a year, if you've had new experiences and formed strong memories, retrospectively that year might feel substantial and long. This suggests a strategy for making life feel longer. Seek out new experiences, break your routines, pay attention, be present, form strong memories. This won't slow down clock time, but it might enrich your experience of time, making your life feel fuller and more expansive. Our bodies also have their own time perception, independent of our conscious minds. We have internal biological clocks called circadian rhythms. These roughly 24-hour cycles regulate when we feel alert and when we feel sleepy, when we get hungry, when our body temperature rises and falls. These circadian rhythms are influenced by external cues, especially light. This is why jet lag happens. When you travel across time zones, your internal clock is still set to your home time. Your body thinks it's time to sleep when the local time says it's afternoon. It takes several days for your circadian rhythms to adjust to the new schedule. Even in the absence of external time cues, your body maintains these rhythms. Studies of people living in environments without clocks or sunlight show that humans naturally settle into roughly 24-hour cycles. We have an internal sense of daily time built into our biology. But circadian rhythms aren't the only biological timers we have. We also have interval timers that help us judge shorter durations. If I ask you to estimate when 30 seconds have passed, you can do it with reasonable accuracy. This ability to judge time intervals is partly learned, but it also seems to be built into how our brains work. Certain brain regions are particularly important for time perception. The basal ganglia, cerebellum, and prefrontal cortex all play roles in how we perceive and estimate time. Damage to these areas can impair time perception. People might lose the ability to accurately judge durations or to properly sequence events. Interestingly, the neurotransmitter dopamine affects time perception. Higher dopamine levels tend to speed up our internal clocks, making external time seem to pass slowly. Lower dopamine levels slow down our internal clocks, making external time seem to pass quickly. This might partially explain why stimulants, which increase dopamine, can make time feel stretched out. Age-related changes in dopamine might also contribute to why time seems to speed up as we get older. Dopamine levels tend to decline with age. If our internal clocks are running slower, external time would appear to move faster by comparison. All of this reveals something remarkable. Time perception is not just passive reception of an external reality, it's an active construction by our brains. Your brain is constantly creating your experience of time, just as it creates your experience of color, sound, and space. This means that time, as you experience it, is partly created by you. Not the objective time measured by clocks. That ticks along regardless of what you think or feel, but subjective time, experiential time, the time you actually live through, that's constructed by your mind, influenced by attention, emotion, memory, and biology. This is why two people can experience the same event and have very different senses of how long it lasted. This is why your perception of time can be so malleable. You're not just living in time. You're creating your experience of time moment by moment. Understanding this can be liberating. If your experience of time is partly constructed, partly under your influence, then you have some agency in how you experience time. You can't stop the clock, but you can potentially enrich your experience, make moments feel more substantial, create memories that make your life feel fuller. As you rest here now, notice your own time perception. Does this moment feel long or short? Are you aware of time passing or absorbed in these ideas? There's no right answer, no correct way to experience this. Just notice gently how time feels to you right now. We've explored how we measure time and how we perceive it. Now let's gently turn our attention to what physics, the science of matter, energy, and the fundamental forces of nature, tells us about time. This is where things become truly fascinating, where our everyday intuitions about time start to shift and expand. For most of human history, time seemed simple and absolute. Time was time. It flowed steadily forward at the same rate everywhere in the universe. Whether you were on Earth or on the Moon, whether you were standing still or moving fast, time passed at the same rate for everyone. This seemed obvious, self-evident, not worth questioning. Then came Isaac Newton. In the 17th century, Newton developed his laws of motion and universal gravitation. These laws explained how objects move, how planets orbit the sun, how apples fall from trees. Newton's physics was remarkably successful, able to predict the motions of celestial bodies with impressive accuracy. Newton's view of time was absolute. He believed in what we might call universal time, a cosmic clock that ticked at the same rate everywhere in the universe. In Newton's universe, time was like a river that flowed at a constant rate, carrying everything along with it. If something happened at a particular moment, that moment was the same moment everywhere for everyone. This made intuitive sense. It matched everyday experience. If two people synchronized their watches and then one traveled to another country, their watches would still show the same time when they reunited. Time seemed to be the same everywhere. For more than 200 years, Newton's absolute time was the foundation of physics. Scientists used it to calculate orbits, predict eclipses, understand motion. It worked beautifully for these purposes, but there were hints, subtle clues, that something wasn't quite right. One of these clues involved light. Scientists in the 19th century discovered that light travels as a wave. Waves need something to wave in. Water waves travel through water, sound waves travel through air. So scientists assumed light waves must travel through some medium. They called this hypothetical medium the luminiferous ether. The ether was supposed to fill all of space. Light waves would ripple through it like waves through water. This seemed reasonable, but it led to a prediction. If the Earth was moving through the ether, then light should travel at different speeds depending on whether it was moving with or against the Earth's motion through the ether. In 1887, two scientists named Albert Michelson and Edward Morley conducted a famous experiment to detect this effect. They measured the speed of light traveling in different directions, expecting to find differences based on Earth's motion. But they found something surprising. The speed of light was the same in all directions, exactly the same. No matter how the Earth was moving, light always traveled at the same speed. This was puzzling. How could light always travel at the same speed regardless of the motion of its source or observer? It didn't make sense according to Newton's physics. If you're on a train moving forward and you throw a ball forward, the ball's speed relative to the ground is your throwing speed plus the train speed. But light doesn't work this way. Light always travels at the same speed, about 300,000 kilometers per second, regardless of how the source is moving. This mystery remained unsolved for nearly 20 years. Then, in 1905, a young patent clerk named Albert Einstein published a paper that revolutionized our understanding of space and time. This paper introduced what we now call special relativity. Einstein started with two simple principles. First, the laws of physics are the same for everyone moving at constant velocity. Second, the speed of light is always the same for all observers, regardless of their motion. These principles seemed reasonable, even obvious, but their consequences were extraordinary. Einstein realized that if the speed of light is always constant, then time itself cannot be absolute. Time must be flexible, relative, different for different observers. This was a radical idea. It contradicted centuries of intuition, but it was necessary to explain the experimental evidence. Here's a simple way to understand it. Imagine you're on a train moving very fast, close to the speed of light. You shine a flashlight forward. Light travels away from you at the speed of light, just as you'd expect. Now imagine someone standing beside the tracks, watching the train pass. They also see the light from your flashlight traveling at the speed of light. But here's the puzzle. From the perspective of the person on the ground, you and your flashlight are already moving forward very fast. If the light is also moving forward at the speed of light relative to you, shouldn't it be moving even faster, relative to the person on the ground? Your speed plus light speed? No. The speed of light must be the same for both observers. The only way this can work is if time itself passes differently for you on the train than for the person on the ground. Time must slow down for you, the moving observer, so that light still moves at the same speed relative to both of you. This effect is called time dilation. The faster you move, the slower time passes for you relative to someone standing still. This isn't an illusion or a trick. Time actually passes more slowly for moving objects. At everyday speeds, walking, driving, even flying in an airplane, the effect is incredibly tiny, far too small to notice. But at speeds approaching the speed of light, the effect becomes dramatic. If you could travel at 90% of the speed of light, time would pass about 44% slower for you than for someone at rest. This leads to fascinating scenarios. Imagine you board a spaceship and travel through space at nearly the speed of light for what feels like 5 years. You then return to Earth. Because time was passing more slowly for you during your high-speed journey, much more than 5 years would have passed on Earth. You might return to find that 50 years had gone by. Your friends would be much older, while you had aged only 5 years. This scenario is sometimes called the twin paradox. If one twin travels at high speed while the other stays on Earth, the traveling twin ages more slowly. When they reunite, the traveling twin is younger. This isn't science fiction. It's a real consequence of special relativity, confirmed by many experiments. We can actually observe time dilation with particles moving at high speeds. Certain unstable particles created in particle accelerators exist for only a tiny fraction of a second before decaying. But when these particles are moving at nearly the speed of light, they last much longer from our perspective. Time is literally passing more slowly for them. GPS satellites provide another example. These satellites orbit Earth at high speeds. Special relativity predicts that time should pass slightly more slowly on the satellites than on Earth's surface. This effect is tiny, only microseconds per day, but GPS systems must account for it to provide accurate location data. Without correcting for relativistic time dilation, GPS would accumulate errors of several kilometers per day. But special relativity only describes time for objects moving at constant speeds. Einstein wondered what happens when objects accelerate, when gravity is involved. This led him to develop general relativity, published in 1915. General relativity extended his ideas about time in even more profound ways. In general relativity, gravity isn't a force pulling objects together, as Newton thought. Instead, gravity is the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space-time around them, and this curvature is what we experience as gravity. Here's where it gets really interesting for our understanding of time. Space-time curvature doesn't just affect space, it affects time too. Strong gravitational fields slow down time. Imagine you're standing near a massive object, like a black hole. The space-time around the black hole is severely curved. Time passes more slowly for you than for someone far away from the black hole. If you spent an hour near the black hole and then traveled back to someone far away, you might find that several hours or even days had passed for them. This gravitational time dilation is real and measurable. Clocks at different altitudes on Earth tick at slightly different rates. A clock on a mountain runs slightly faster than a clock at sea level because it's further from Earth's mass, experiencing weaker gravity. The difference is tiny, only nanoseconds per day, but atomic clocks are precise enough to measure it. This has been verified in many experiments. In one experiment, scientists placed atomic clocks at different floors of a building. The clock on the higher floor ran faster than the clock on the lower floor, exactly as general relativity predicted. Every floor you go up, time passes slightly faster. This means that you're actually aging faster when you're standing up than when you're lying down. The difference is infinitesimal, far too small to ever notice, but it's real. Your head ages slightly faster than your feet because it's slightly further from Earth's center. Near extremely massive objects like neutron stars or black holes, gravitational time dilation becomes extreme. If you could somehow survive orbiting close to a black hole, time might pass so slowly for you that you could watch billions of years pass in the wider universe in what feels like hours to you. This isn't theoretical speculation. We observe effects consistent with this. Matter falling into black holes appears to slow down and freeze at the event horizon from our perspective, because time dilation becomes infinite at that boundary. So what special and general relativity tell us is that time is not absolute. Time is relative. It depends on how fast you're moving and how strong the gravitational field is where you are. There's no universal now that applies everywhere in the universe. Different observers, in different states of motion or different gravitational fields, experience time at different rates. This seems to contradict our everyday experience. We feel like there's one present moment that applies to everyone, but physics tells us this is an illusion. The present moment is local, personal, relative. Here's another mind-bending consequence of relativity. Simultaneity is relative. Events that appear to happen at the same time for one observer might happen at different times for another observer, moving relative to the first. Imagine two events happen far apart in space, say a light turning on in New York and another light turning on in Los Angeles. If these events are carefully timed to be simultaneous for someone standing still, they will not be simultaneous for someone moving at high speed. The moving observer might see the New York light turn on first, or the Los Angeles light turn on first, depending on their direction of motion. This isn't just a matter of when the light reaches the observer. Even accounting for light travel time, Different observers genuinely disagree about which event happened first. There's no absolute answer to the question, which happened first? It depends on your frame of reference. Of course, this only matters for events that can't causally influence each other, events far enough apart that light couldn't travel between them in time. For events connected by cause and effect, the order is preserved. Causes always precede effects for all observers. But for events that are causally disconnected, their temporal order is relative. All of this reveals something profound about the nature of time. Time is not separate from space. They're interwoven into a single four-dimensional fabric called space-time. Events don't happen in space at a particular time. Events happen in space-time at particular locations in this four-dimensional continuum. We experience space-time as separate dimensions, three of space, one of time, because we're moving through it in a particular way. But fundamentally, space and time are aspects of the same thing. Just as you can rotate your perspective to see different aspects of a three-dimensional object, changing your velocity or gravitational situation gives you different perspectives on space-time, different divisions between space and time. This unity of space and time is one of the most beautiful insights of modern physics. It reveals that the universe is even more elegant and interconnected than we imagined. Space and time, which seem so different in our daily lives, are intimately related at a fundamental level. Let's rest here for a moment with these ideas. Time is flexible. It passes at different rates depending on motion and gravity. There's no absolute present moment shared by everyone. Space and time are unified into space-time. These ideas might seem strange, abstract, disconnected from everyday life, and in a sense, they are. At the speeds we move, and in Earth's relatively weak gravity, relativistic effects are negligible. For practical purposes, Newton's absolute time works fine. But these ideas are also deeply real. They describe how the universe actually works. GPS satellites must account for relativity. Particle accelerators observe time dilation daily. These aren't just mathematical curiosities, they're features of reality. And philosophically, they change how we think about time. Time is not a fixed container in which events occur. Time is part of the dynamic fabric of the universe itself. Time is influenced by matter and energy. Time is relative, flexible, interwoven with space. This doesn't mean time is unreal or purely subjective. Time is very real. Events do happen in sequence. Causes precede effects. The future is different from the past, but the nature of time is more subtle, more interesting, more interconnected than our intuitions suggest. As you rest here, you are situated in space-time. You're moving through time at the rate of 1 second per second, as everyone does from their own perspective. But relative to someone moving very fast, or someone in a very different gravitational field, your time is passing at a different rate. You're both experiencing time normally from your own perspectives, but you're experiencing it differently from each other. This is the universe we live in. A universe where time is woven into the fabric of reality itself, where time bends and flexes with the geometry of space-time, where the simple ticking of a clock is influenced by motion and gravity in ways that Newton never imagined. We've seen that time is relative, that it's woven together with space, that it passes at different rates depending on motion and gravity. But there's another profound mystery about time that we haven't yet addressed. Its direction. Time has an arrow. It points one way. We call this the arrow of time. Think about your everyday experience. You remember the past, but not the future. You can influence the future through your actions, but you cannot change the past. Events unfold in a particular sequence. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. People are born, grow old, and die. Never the reverse. This seems so obvious that you might wonder why it needs explaining. Of course, time goes forward. How could it be otherwise? But here's the puzzle. The fundamental laws of physics don't distinguish between forward and backward in time. They're time-symmetric. Let me explain what this means. Take Newton's laws of motion or Einstein's equations of general relativity. These equations work equally well whether time is running forward or backward. If you filmed a planet orbiting the Sun and then played the film backward, the backward motion would still obey the laws of physics perfectly. The equations don't care which direction time is flowing. Even at the quantum level, most physical laws are time-symmetric. The interactions between particles work the same way forward and backward in time. If you could watch a particle interaction and then watch it in reverse, both would be valid according to the laws of physics. And yet clearly, time does have a direction in our experience. Things happen in a particular order. Processes unfold one way but not the other. So where does this arrow of time come from? Why does time seem to flow in one direction if the fundamental laws don't require it? This is one of the deepest questions in physics, and it connects to a concept called entropy. Entropy is a measure of disorder, of randomness, of how spread out and mixed up things are. And there's a law of physics, the second law of thermodynamics, that says entropy always increases over time. Let's think about this gently with some examples. Imagine you have a box divided in half by a removable partition. On one side of the partition, you have a gas, let's say air molecules bouncing around. On the other side, you have a vacuum, nothing at all. The molecules are all confined to one half of the box. This is an ordered state, a low entropy state. Now you remove the partition, what happens? The air molecules spread out to fill the entire box. They don't stay confined to one side. They diffuse, spreading evenly throughout the available space. The gas goes from being concentrated in one place to being dispersed everywhere. This is a higher entropy state, a more disordered state. Here's the key point. You will never see the reverse happen spontaneously. You will never see all the air molecules in a box randomly decide to gather in just one half, leaving a vacuum in the other half. It's not that this is impossible according to the laws of physics. It's just extraordinarily unlikely. The number of ways molecules can be arranged to fill the whole box is vastly greater than the number of ways they can be arranged to fill only half the box. This illustrates the second law of thermodynamics. In isolated systems, entropy tends to increase. Things tend to become more disordered, more spread out, more mixed up, and this tendency gives time a direction. Think about other examples. A drop of ink in water spreads out. The ink molecules diffuse through the water until the color is evenly distributed. You never see the opposite, evenly distributed ink suddenly gathering back into a concentrated drop. An ice cube in warm water melts. The cold water molecules from the ice mix with the warm water molecules until everything is the same temperature. You never see warm water spontaneously separate into ice-cold and very warm regions. A broken egg on the floor is a high entropy state. The shell is in pieces. The yolk and white are spread out and mixed with air. An intact egg in your hand is a low entropy state. Everything is organized, contained, structured. Eggs break easily, going from low entropy to high entropy. But scrambled eggs on the floor never reassemble themselves into whole eggs. All of these processes have a direction. They go from lower entropy to higher entropy, from more organized to more disordered. And this direction defines the arrow of time. The future is the direction of increasing entropy. But why does entropy increase? This is where things get subtle and interesting. Entropy increases because there are simply more ways for things to be disordered than ordered. It's a statistical effect, a consequence of probability. Imagine you have a deck of cards. There's only one way to arrange the deck in perfect order, ace through king in each suit. But there are millions and millions of ways to arrange the deck in disorder, random shufflings. If you shuffle the deck, you're vastly more likely to produce a disordered arrangement than an ordered one, simply because there are so many more disordered arrangements possible. Similarly, for any physical system, there are typically many more high entropy states than low entropy states. So if a system is free to evolve, it will most likely evolve toward higher entropy, simply because that's where most of the possible states are. This doesn't mean entropy must always increase in every tiny region at every moment. Local decreases in entropy can and do happen. When you organize your desk, you're decreasing the entropy of that space. When living things grow and develop, they're creating local order. But these local decreases are always accompanied by larger increases elsewhere. When you organize your desk, you're using energy from food, which came from plants, which captured energy from the sun. The sun is radiating enormous amounts of energy into space, increasing the universe's total entropy by far more than the tiny decrease you created by tidying your desk. The overall entropy still increases. Living things are fascinating examples of local entropy decrease. A living organism is highly organized, highly structured, low entropy compared to random arrangements of the same molecules. But living things maintain this organization by consuming energy and producing waste, heat, and disorder in their environment. The total entropy of the system, organism plus environment, still increases, so the second law of thermodynamics isn't violated by local organization. It just means that the total entropy of the universe keeps increasing. And this increase gives time its arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because memory formation requires entropy increase. We can influence the future, but not the past, because causes increase entropy and effects reflect that increase. The asymmetry between past and future comes from the entropy gradient. But this raises a profound question. Why was entropy low in the past? If entropy always increases, and if we look backward in time, entropy must have been lower and lower the further back we go. Ultimately, if we go all the way back to the beginning of the universe, entropy must have been extremely low. This is puzzling because low entropy states are rare, unlikely, special. Why would the universe begin in such a special, organized low entropy state? This is called the past hypothesis, the assumption that the universe began with very low entropy. But we don't fully understand why this should be true. The Big Bang, the beginning of our universe about 13.8 billion years ago, was indeed a state of extremely low entropy. The early universe was remarkably uniform, with matter and energy distributed very evenly. This might sound like high entropy. Isn't uniformity a kind of disorder? But actually, for a gravitating system, uniform distribution is low entropy. In a gravitating system, high entropy means clumping. Gravity pulls matter together into dense structures, stars, galaxies, black holes. The early universe, with its smooth, even distribution of matter, was far from gravitational equilibrium. It was in a special, low-entropy state. And ever since, entropy has been increasing as matter clumps together under gravity, forming the cosmic structures we see today. This low-entropy beginning is, in a sense, the origin of time's arrow. If the universe had started in a high-entropy state, already at equilibrium, nothing interesting would happen. There would be no change, no processes, no arrow of time. It's because the universe started in a special low-entropy state that time has a direction, that change happens, that the universe evolves. But why did the universe start that way? We don't have a complete answer. This is one of the deepest open questions in cosmology and physics. Some scientists think there might be a deeper explanation involving quantum gravity or the physics of the Big Bang itself. Others think the low-entropy beginning might just be a brute fact about our universe, something we have to accept without further explanation. There's another fascinating aspect of the arrow of time, its connection to causality. We're used to thinking that causes precede effects. You flip a switch, and then the light turns on. The switching is the cause, the lighting is the effect, and the cause comes first in time. But the fundamental laws of physics are time-symmetric, as we said. They don't inherently distinguish cause from effect. In principle, you could have effects that precede their causes, running backward in time. So why do we always see causes before effects? The answer again relates to entropy. Causes are typically low entropy, organized events that lead to high entropy, disorganized effects. This gives causality a direction that aligns with the arrow of time. Low entropy states naturally lead to high entropy states, not the reverse, so causes naturally precede effects. Think about ripples spreading on a pond. You throw a stone, the cause, and ripples spread outward, the effect. The stone creates an organized, localized disturbance. The ripples are the dissipation of that organization, the spreading of that energy into disorder. This process goes from low entropy to high entropy, from past to future. You never see the opposite. Ripples converging from all directions on the pond, organized so perfectly that they propel a stone upward out of the water into your hand. This would be time-reversed causality. It's not forbidden by fundamental physics, but it would require an incredibly special, low-entropy arrangement of all those ripples, which is astronomically unlikely. So our everyday experience of causality, causes preceding effects, is actually a consequence of the second law of thermodynamics. It's another manifestation of time's arrow. This has profound implications for our understanding of time. Time's direction isn't built into the fundamental laws of physics at the deepest level. It emerges from statistical properties, from the fact that the universe started in a low-entropy state and has been evolving toward higher entropy ever since. In a sense, the arrow of time is cosmological. It's a feature of our universe's history, not an absolute necessity of physics. In a different universe that somehow started in a high-entropy state, there might not be an arrow of time. Or in a distant future, when the universe reaches maximum entropy, a state sometimes called heat death, the arrow of time might cease to have meaning. Let's think about this heat death scenario for a moment, very gently. If entropy keeps increasing, eventually the universe will reach a state of maximum entropy. All energy will be evenly distributed. All processes will have run their course. Nothing will change anymore. In this ultimate equilibrium state, there would be no arrow of time. The future would look the same as the past. Nothing would happen to distinguish one moment from another. Time would still exist, perhaps, but it would be meaningless, featureless, without direction. This sounds bleak, and in a sense it is, but it's also very far in the future, many trillions of years from now. For the foreseeable future, the universe has plenty of room for entropy to increase, plenty of scope for interesting processes to unfold. And it's worth noting that we don't know for certain that heat death is the universe's fate. Our understanding of cosmology is still developing. There might be twists we haven't anticipated, but given our current knowledge, eventual heat death seems likely. For now, though, we live in a universe where time has a clear direction. Entropy increases. Causes precede effects. The past is different from the future, and this asymmetry makes possible all the rich complexity of the world around us. Stars shine because they're in low-entropy organized states, burning fuel and radiating energy. Living things exist because they can harness energy flows to maintain their organization. Consciousness and thought require processes that unfold in time, that record and process information, that remember the past. All of this depends on time's arrow. In a universe without an entropy gradient, without a direction to time, none of this would be possible. There would be no change, no life, no consciousness, no experience. So while the arrow of time might seem like a simple, obvious feature of reality, it's actually profound and subtle. It emerges from statistical mechanics and thermodynamics. It depends on the special initial conditions of our universe. It gives structure and meaning to our existence. As you rest here, you are part of this great cosmic process. Your body maintains its organization by consuming energy and producing entropy. Your thoughts unfold in time, each moment following the last, moving from past to future. You remember what was and anticipate what will be. You are experiencing time's arrow directly. This arrow is what makes your experience possible. It's what allows change, growth, learning, living. Without it, there would be no story, no journey, no life unfolding through time. We've explored time's nature, its flexibility, its direction. Now let's turn our attention to perhaps the most fundamental question of all. Did time have a beginning? Was there a first moment? Or has time stretched backward infinitely into the past? For much of human history, people had different answers to this question depending on their culture and Beliefs. Some ancient philosophies viewed time as eternal and cyclical, with no beginning or end. The universe went through endless cycles of creation and destruction, like seasons repeating forever. Other traditions believed in a definite creation event, a moment when time itself began along with the universe. In many religious cosmologies, a divine act of creation marked the beginning of time. Before that moment, there was no before. Time itself came into existence with the universe. For a long time, these were primarily philosophical and theological questions. Science had little to say about the ultimate origin of the universe or of time itself. That changed in the 20th century, with developments in astronomy and physics. The story begins with observations of distant galaxies. In the 1920s, astronomer Edwin Hubble made a remarkable discovery. He found that distant galaxies are moving away from us. Not just a few galaxies, but all of them, in every direction. The universe is expanding. This wasn't just a matter of galaxies moving through space. Space itself is expanding, carrying the galaxies along with it. The distances between galaxies are increasing because the fabric of space is stretching. This discovery had profound implications. If the universe is expanding now, it must have been smaller in the past. If you imagine running time backward, the galaxies get closer together. Go back far enough, and everything in the universe must have been compressed into an incredibly small, dense, hot state. This realization led to what we now call the Big Bang theory. According to this theory, the universe began approximately 13.8 billion years ago in an extremely hot, dense state and has been expanding and cooling ever since. Everything we see, all matter, all energy, all of space itself, emerged from this initial state. But here's what matters for our discussion of time. The Big Bang wasn't just the beginning of matter and energy. It was the beginning of time itself. Before the Big Bang, there was no before. Time began with the Big Bang. This is a difficult concept to grasp. We're used to thinking of events happening in time. We ask, what happened before for any event? But the Big Bang is unique. It's not an event in time. It's the beginning of time. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't quite make sense because before requires time, and time didn't exist before the Big Bang. Einstein's general relativity helps us understand this. In general relativity, space and time are part of space-time, and space-time itself is dynamic. It can curve, expand, contract. The Big Bang represents a boundary of space-time, a point where space-time itself begins. There's no space-time before that point, so there's no before in any meaningful sense. Evidence for the Big Bang comes from multiple sources. The expansion of the universe, which we can observe directly, is one piece of evidence. Another is the cosmic microwave background radiation, a faint glow of light that fills all of space, left over from when the universe was very young and very hot. This radiation was predicted by Big Bang theory and discovered in 1964. It's like an echo of the Big Bang itself, a fossil remnant from the early universe. By studying this radiation carefully, scientists have learned an enormous amount about the universe's history, age, and composition. The Big Bang theory has been refined and tested over decades. It's now the standard model of cosmology, accepted by the vast majority of scientists who study the universe's history. But it still leaves many questions unanswered, particularly about the very beginning. The mathematics of general relativity suggests that, at the moment of the Big Bang, the universe was compressed to a point of infinite density, what we call a singularity. At this singularity, our current physics breaks down. The equations give infinite answers, which is usually a sign that we're missing something important. We don't actually know what happened at the very first instant. Our best theories can describe the universe from a tiny fraction of a second after the Big Bang onward, but that first instant itself remains mysterious. To truly understand it, we would need a theory of quantum gravity, a theory that combines quantum mechanics with general relativity. We don't yet have such a theory. Some physicists think that quantum effects might eliminate the singularity. Perhaps the universe didn't actually begin at a point of infinite density. Perhaps quantum mechanics smooths out that extreme beginning into something more gentle, something our mathematics can handle. There are various proposals for what this might look like. Some involve the universe bouncing from a previous contracting phase rather than beginning from nothing. Others involve quantum fluctuations creating universes from vacuum states. Still others suggest that time itself might be quantized near the Big Bang, made up of discrete chunks rather than flowing continuously. These ideas are highly speculative, pushing at the edges of our knowledge. They're attempts to understand something that might be fundamentally beyond our current physics, but they share a common theme. They take seriously the idea that time itself had a beginning, that there really was a first moment. This raises deep philosophical questions. If time had a beginning, what does that mean? How can something begin to exist when there's no time for it to begin in? These questions touch on the nature of causality, existence, and creation itself. Some philosophers and scientists argue that the question, why is there something rather than nothing, becomes even more puzzling if time had a beginning. If there was no time before the universe, then the universe didn't come from anything. It wasn't caused by anything. It simply is, existing with its own beginning built in. Others find this perfectly acceptable. Perhaps causality only makes sense within time. Perhaps asking for a cause of time itself is a category error, like asking for the color of mathematics or the smell of justice. Time is the framework within which causes operate. It doesn't need a cause itself. Let's think about this from another angle. In our everyday experience, everything has a beginning. You were born. This building was constructed. The earth formed. We're used to things starting at particular moments in time. But time itself is different. It's not a thing within time. It's the dimension within which things exist and events occur. If time had a beginning, it's unique among beginnings. It's not like other starting points. It's the starting point of starting points, the first moment that makes all other moments possible. Some religious thinkers have found the Big Bang consistent with creation narratives. The idea of a definite beginning, a moment when everything came into existence, resonates with traditional beliefs about divine creation. Others see the Big Bang as a purely natural process, requiring no supernatural explanation. Physics itself is neutral on such questions. It describes what happened, not why it happened, or what deeper meaning it might have. The Big Bang theory tells us that the universe, including time, had a beginning about 13.8 billion years ago. It doesn't tell us whether there's purpose or meaning behind that beginning. There's also the question of whether the Big Bang was truly the beginning of everything, or just the beginning of our observable universe. Some theories propose that our universe is part of a larger multiverse, a vast collection of universes, each with its own Big Bang, its own properties, perhaps even its own laws of physics. In such scenarios, our Big Bang might be one event among many in some larger cosmic structure. Time in this larger structure might extend beyond our Big Bang, with our universe's timeline being just one branch or bubble in a more extensive temporal framework. These multiverse ideas are controversial and difficult to test. By definition, other universes would be beyond our ability to observe. They might be interesting theoretical possibilities, but whether they're real is harder to establish. Still, they remind us that our understanding of time's beginning might not be complete. There might be layers of reality we haven't yet discovered. For practical purposes, though, the Big Bang represents the beginning of everything we can observe and interact with. All the matter and energy we see, all the space we can measure, all the time we can trace. It all traces back to that moment 13.8 billion years ago. Think about what this means. Every atom in your body was forged in stars that lived and died over billions of years. Those atoms emerged from processes that began with the Big Bang. The carbon in your bones, the oxygen you breathe, the iron in your blood, all of it has a history stretching back to the beginning of time. You are made of ancient matter, matter that has existed in various forms since shortly after time itself began. The atoms have been recycled through countless stars, planets, and living things, but their ultimate origin is that first moment when time started and the universe burst into existence. This gives us a deep connection to the cosmos. We're not separate from the universe looking in. We're part of it, made of the same stuff, following the same physical laws, embedded in the same space-time that began with the Big Bang. The beginning of time also has implications for how we think about time's nature. If time had a beginning, it's not an eternal, unchanging backdrop. It's part of the dynamic, evolving universe. Time emerged along with space, matter, and energy. It's woven into the fabric of physical reality. This means time is contingent. It didn't have to exist. There could have been nothing, no space, no time, no matter, no energy. The fact that something exists rather than nothing, that time exists rather than timelessness, is profound and perhaps ultimately mysterious. As you lie here peacefully, consider that you exist approximately 13.8 billion years after the beginning of time. 13.8 billion years of cosmic history have unfolded to reach this moment. Galaxies have formed and evolved. Stars have ignited and died. Planets have coalesced from cosmic dust. Life has emerged and diversified. And now you're here, conscious and aware, thinking about time itself. This present moment is the leading edge of that vast cosmic unfolding. Behind you stretches nearly 14 billion years of history. Ahead of you stretches an unknown future. But this moment, this now, is where history has arrived. Everything that has happened since the Big Bang has led to this exact moment. There's something both humbling and awe-inspiring about this perspective. We're tiny in space and time, brief flickers of consciousness in a vast cosmos, and yet we're also connected to everything, participants in the grand story of the universe itself. The beginning of time is the beginning of that story. It's where everything starts, not just matter and energy, but possibility itself. Before the Big Bang, there were no moments, no events, no change, no becoming. With the Big Bang, time began, and with time came the possibility of everything that has happened since. We don't fully understand why the Big Bang happened, or whether why even makes sense as a question. We don't know if it was the absolute beginning of everything, or just the beginning of our local cosmic patch. We don't know if time will have an end as it had a beginning. But we do know this. Time is real, time began, and time has been flowing forward ever since, carrying the universe through its grand evolution from that initial moment to the present day. We exist within that flow, brief participants in an ancient story that began when time itself began. We've journeyed from time's measurement to its beginning. Now let's settle into perhaps the most intimate aspect of time, the present moment. Right now, this instant. The ever-fleeting now that we're always experiencing but can never quite hold on to. The present moment is where we live. You cannot experience the past directly. It's gone, existing only in memory and physical traces. You cannot experience the future directly. It hasn't happened yet, existing only in imagination and possibility. All you ever experience is now, this moment, this present. And yet, when you try to examine the present moment closely, it becomes elusive. What exactly is now? How long does it last? Where does the present begin and end? If you try to pin down the present moment precisely, you run into problems. Is the present a single instant with no duration? If so, it would have no length at all, no temporal extent. It would be infinitely thin, lasting zero time. But how can you experience something with no duration? On the other hand, if the present has some duration, say a second or a fraction of a second, then part of it is already past by the time the rest of it arrives. The beginning of that second has already happened before the end of it occurs. So which part is really now? This puzzled troubled philosophers for centuries. St. Augustine, whom we mentioned earlier, wrote about this paradox. If the past is gone and the future hasn't arrived and the present has no duration, then where is time? How can time exist if none of its parts, past, present, or future, seem to have substantial reality? Modern neuroscience has given us some insights into how we experience the present. Our brains don't process information instantaneously. There's a delay between when something happens and when we become conscious of it. Light enters your eyes, sound enters your ears, but it takes time, a few hundredths of a second, for your brain to process these signals and create your conscious experience. What you experience as now is actually a very recent past, a few milliseconds ago. Your brain stitches together inputs from different senses, which arrive at different speeds, and presents them to your consciousness as a unified present moment. In a sense, you're always living in the very recent past, though the delay is so small you never notice it. But there's more to the present than just neural processing delays. Your brain also creates what we might call the specious present, a psychological now that has some duration. This is the window of time that feels present to you, the span within which events seem to be happening now rather than in the past. This psychological present is typically estimated to last somewhere between half a second and a few seconds. Within this window, events feel simultaneous, part of the same now. A spoken sentence feels present as it unfolds. A melody flows through a psychological present that encompasses several notes at once. This extended present makes sense from an evolutionary perspective. To navigate the world effectively, you need to perceive events in their immediate context, not as isolated instants. When you catch a ball, you're responding to its trajectory over a brief span of time, not to a single frozen instant. Your sense of an extended present allows you to perceive motion, rhythm, and sequential patterns. Different activities seem to have different durations of presentness. When you're engaged in conversation, the present might feel like it extends across several seconds, the current sentence, the immediate context of what's being said. When you're listening to music, the present might encompass several measures, a phrase of melody. When you're in danger or highly alert, the present might compress to a shorter duration as your attention sharpens. When you're relaxed and unfocused, the present might expand, becoming more diffuse and extended. So the present moment isn't a fixed thing. It's partially constructed by your brain, varying in its experience duration depending on context and mental state. The now you experience is not an objective feature of time, but a subjective window your consciousness creates. But let's consider the present from a physics perspective. According to relativity, as we discussed earlier, simultaneity is relative. Events that are simultaneous for one observer aren't necessarily simultaneous for another observer in motion. This means there's no universal present moment shared by everyone in the universe. You have your present moment, the events happening now from your perspective. Someone else moving at a different velocity has a different present moment. Your now and their now are different slices through space-time. Imagine you're looking at a distant star. You see the light that left that star years ago. You're seeing the star's past, not its present. But from the star's perspective, if it could have a perspective, there would be some event happening right now. Your now and the star's now are different. Even more strangely, if an alien on a distant planet were moving at high speed relative to Earth, the set of events they would consider now might include things in your future or your past, depending on their direction of motion. Their present slice through space-time tilts differently than yours. This suggests that the present moment, like simultaneity, is not absolute, but relative. The now is observer-dependent. It's a feature of your particular perspective on space-time, not an objective division of reality. Some physicists and philosophers take this even further. They suggest that past, present, and future all exist equally in space-time. This is called the block universe view, or eternalism. According to this perspective, all moments in time exist simultaneously in the four-dimensional structure of space-time. The past hasn't ceased to exist, and the future already exists. They're just located at different positions in the time dimension, just as distant places are located at different positions in space. From this view, time doesn't flow. The appearance of flow, the feeling that time passes, is an illusion created by our consciousness moving through space-time. We experience moments sequentially, one after another, and this creates the sensation of time passing. But objectively, all moments simply exist at their respective positions in space-time. This view is supported by relativity's treatment of space-time as a unified four-dimensional structure. If space and time are truly unified, and if there's no absolute present moment, then perhaps all times are equally real, just as all places are equally real, even when we're not currently at them. The block universe view has philosophical implications. If the future already exists in some sense, does that mean everything is predetermined? If all moments exist eternally in space-time, what happens to free will, to genuine choice, to open possibilities? These are deep questions without easy answers. Some argue that even in a block universe, free will could exist within the structure. Your choices are real features of space-time, even if they're fixed from a timeless perspective. Others find the block universe view incompatible with genuine freedom and openness. There's an alternative view called presentism, which holds that only the present moment exists. The past has ceased to exist, having been real, but now gone. The future doesn't exist yet. Only the present is real. Time truly flows, with reality constantly shifting from one moment to the next. Presentism aligns more closely with our intuitive experience. It feels like only the present is real, like the past is gone and the future hasn't arrived. It makes sense of why we can't interact with the past or future. They literally don't exist. But presentism faces challenges from relativity's relative simultaneity. If different observers have different present moments, which one is the real present? A middle view, called the growing block universe, suggests that the past and present exist, but the future doesn't yet. Reality grows as time progresses, with new moments coming into existence at the leading edge of the present. This preserves some sense of temporal flow and becoming, while acknowledging the reality of the past. Which of these views is correct? We don't know. They represent different philosophical interpretations of the same physical facts. Physics tells us about space-time structure, about how time behaves, but it doesn't definitively answer whether past and future are real or whether only the present exists. For our experience, though, these abstract debates take a back seat to the lived reality of the present moment. Whatever the ultimate metaphysics, you experience life in the now. This moment is where your consciousness resides. This is where you feel, think, perceive, and act. The present moment is also where change happens. You can't change the past. It's fixed, already written. You can't directly affect the future, it hasn't happened yet. But the present is where possibilities collapse into actualities, where the open future becomes the fixed past. In the present, you make choices, take actions, cause things to happen. This makes the present moment special, regardless of whether all times exist equally in space-time. The present is the active edge of reality, where cause leads to effect, where agency operates, where life unfolds. Mindfulness practices in various traditions emphasize the importance of being fully present. Instead of dwelling on past regrets or future anxieties, these practices encourage attention to the current moment. Notice your breath, feel your body, observe your surroundings. Be here now. There's wisdom in this emphasis. Much of human suffering comes from being mentally absent from the present, lost in thoughts about other times. The present moment, when we attend to it fully, is often peaceful, even when circumstances are difficult. It's our thoughts about past and future that create much of our mental distress. Being present doesn't mean ignoring past and future entirely. We learn from the past and plan for the future. Memory and anticipation are valuable cognitive abilities. But there's a difference between useful reflection and being trapped in time-focused rumination. The present moment is also where beauty and meaning are directly experienced. You can remember a beautiful sunset, but you experience its beauty in the present. You can anticipate a joyful reunion, but you feel the joy in the present when it happens. All direct experience occurs now. This gives the present a kind of primacy in human life. Whatever the ultimate nature of time, whatever exists in space-time's structure, your life is lived in a sequence of present moments. Each one is where you exist, where you're conscious, where you're alive. Think about this present moment right now. You're lying comfortably, breathing steadily, listening to these words. This moment has a particular quality, a particular feel. It won't come again. In a few seconds, it will be part of the past, replaced by new present moments. And yet, there's always a present moment. As each now becomes past, a new now takes its place. You're always in the present, even though the present is always changing. It's like standing in a river. The water flowing past you changes constantly, but you're always standing in the river. This might seem paradoxical. The present is fleeting, ephemeral, constantly vanishing into the past. And yet, it's eternal. There's always a present moment. You're always experiencing now, even though now keeps changing. Perhaps this paradox reveals something deep about time's nature. Time is both change and continuity, both flow and permanence. Moments pass, but there's always a moment. The particular present changes, but the fact of presentness remains. As you rest here, you might notice that the present moment has a kind of spaciousness. When you're not caught up in thoughts about past or future, when you're simply present, the now can feel expansive. It's not cramped or hurried. There's room in this moment for whatever arises, sensations, sounds, thoughts, feelings. This spacious present is perhaps closest to the pure experience of time, unfiltered by concepts and analysis. It's time as lived, rather than time as theorized. And in this lived experience, the present moment is complete in itself. It doesn't need past or future to be real. It simply is. The present moment, as we've seen, is where we live. But our experience of time would be profoundly different, perhaps impossible, without memory. Memory connects us to the past. It gives our lives continuity. It makes us who we are. Let's explore gently the deep relationship between time and memory. Think about what your life would be like without memory. Every moment would be completely new, disconnected from all previous moments. You wouldn't recognize anyone. You wouldn't know your own name. You wouldn't remember what you did a second ago, or why you're where you are. Each instant would be isolated, with no connection to anything before it. This isn't just a thought experiment. There are rare cases of people with severe amnesia who live something like this. They can't form new memories. Each conversation feels like the first conversation they've ever had. They meet the same people repeatedly, but never remember meeting them before. Their present moment is untethered from their past. These cases reveal how essential memory is to normal human experience. Memory is what makes you you, your sense of personal identity, who you are, where you've been, what you care about, is built from memories. Without memory, you would have no continuity of self across time. Memory also gives structure to time itself. Without memory, there would be no past. Not for you, at least. The past exists for us, primarily through memory. Yes, there are physical traces of the past in the world, old photographs, historical records, geological layers. But these are meaningful only because we can remember how to interpret them. Remember that there was a past. Your memories create your personal past. The events you remember are the events that make up your history. Things you've forgotten might as well not have happened, at least from your subjective perspective. Your remembered past is your experienced past. But memory is not simply a recording device. It doesn't work like a video camera, faithfully capturing everything that happens. Memory is reconstructive. Each time you remember something, your brain reconstructs that memory from pieces stored in various locations. And each reconstruction can change the memory slightly. This means memories are malleable. They can be altered, distorted, even created where nothing existed before. Studies have shown that people can develop false memories, vivid recollections of events that never actually happened, through suggestion and imagination. This might sound disturbing. If memories can be wrong, how can we trust our past? But it's important to understand that most memories are reasonably accurate, especially for significant events and general patterns. Memory works well enough for us to navigate life effectively. It's not perfect, but it's functional. The reconstructive nature of memory also serves a purpose. Memory isn't primarily about preserving a perfect record of the past. It's about learning from the past to navigate the present and future. Memories that get reinforced are typically ones that were important or useful. Trivial details fade because they're not worth the brain's limited storage capacity. Think about a typical day from several years ago. You probably can't remember specific details, what you ate for lunch, what you wore, what the weather was like. These details weren't important, so your brain didn't prioritize storing them. But you probably do remember significant events from years ago, a wedding, a graduation, a moment of loss or joy. These mattered, so they were encoded more strongly. Memory also compresses time. When you remember a period from your past, say a summer vacation, you don't remember every moment. You remember highlights, significant events, emotional peaks. The hours of ordinary time between memorable moments are compressed or forgotten. Your memory of that summer is like a highlight reel, not a complete recording. This compression is why the past can sometimes feel shorter in retrospect than it did while you were living it. A week-long vacation might have felt long while you were experiencing it, but when you remember it later, it condenses into a few key memories. The experience duration and the remembered duration are different. There are different types of memory, each relating to time in different ways. Episodic memory is memory for specific events, things that happened at particular times and places. Your first day of school, your last birthday, what you had for breakfast this morning. These are episodic memories tied to specific moments in time. Semantic memory is memory for facts and general knowledge, things you know but don't remember learning. You know that Paris is the capital of France, but you probably don't remember the specific moment you learned this fact. Semantic memory is less tied to particular times. Procedural memory is memory for skills, how to ride a bicycle, how to type, how to swim. These memories are encoded in your nervous system and muscles. You might not be able to explain how you balance on a bicycle, but your body remembers. Procedural memories develop over time through practice, but aren't associated with specific moments. Working memory is very short-term memory, the information you're holding in mind right now. When you read a sentence, working memory holds the beginning of the sentence in mind until you reach the end. Without working memory, you couldn't comprehend language or follow a line of thought. All these forms of memory shape your relationship with time. Episodic memory lets you travel mentally backward in time, revisiting past experiences. Semantic memory gives you accumulated knowledge independent of time. Procedural memory carries past learning into present action. Working memory creates continuity within the present moment. The ability to remember the past goes hand in hand with the ability to imagine the future. Brain imaging studies show that remembering past events and imagining future events activate very similar brain regions. This makes sense. Both involve constructing mental scenarios that aren't currently present. When you imagine the future, you're essentially using your memories to simulate what might happen. You draw on past experiences to envision possible futures. Someone with severe amnesia often also loses the ability to imagine future scenarios in detail. Without a remembered past, the imagined future becomes vague and impoverished. This connection between memory and imagination reveals something interesting. Your mind doesn't just exist in the present. It can travel in time, mentally visiting the past through memory and the future through imagination. This mental time travel is one of humanity's remarkable cognitive abilities. Other animals have memory, of course. A dog remembers where it buried a bone. A bird remembers migration routes. But human memory seems to have a special character. We remember not just what happened, but when it happened, and how events relate to each other in time. We construct narratives about our lives, stories that unfold through time. This narrative aspect of memory is crucial to human identity. You understand yourself through the story of your life. Where you came from, what you've experienced, how you've changed. These form the narrative that defines who you are. And this narrative is built from memories arranged in temporal sequence. Interestingly, not all memories are equally accessible. Some memories are vivid and easily recalled. Others are hazy, requiring effort to bring to mind. Still others are apparently lost, though sometimes can be triggered by the right cue, a smell, a song, a particular place. Marcel Proust wrote beautifully about involuntary memory, memories suddenly triggered by sensory experiences. In his famous example, the taste of a madeleine cake dipped in tea brought back a flood of childhood memories. The sensory cue bypassed conscious effort and directly accessed stored memories. These involuntary memories can feel especially vivid and emotional. They arrive unbidden, sometimes bringing with them the entire atmosphere of a past time. The boundary between past and present seems to blur for a moment. You're not just remembering, you're almost reliving. Memory is also selective in another way. We tend to remember emotionally significant events more strongly than neutral ones. This is adaptive. Important events are worth remembering because they might be relevant in the future. But it also means our memory of the past is skewed toward emotional peaks and valleys. This is sometimes called the peak-end rule. When evaluating a past experience, we tend to weight the most intense moments and the ending most heavily. The average level of experience throughout the event matters less than these highlights. This is why a vacation can be remembered fondly, even if much of it was ordinary, as long as there were some peak experiences and a good ending. Memory also changes with age. Young children have limited long-term memory. Most people don't remember events from before age 3 or 4, a phenomenon called childhood amnesia. As we age through childhood and adolescence, memory systems mature and become more sophisticated. In older age, some types of memory decline while others remain stable. Episodic memory, memory for recent events, often weakens. Older adults might have trouble remembering where they put their keys or what they had for lunch yesterday. But semantic memory, general knowledge, usually remains intact. An older person might forget recent conversations, but still remember historical facts learned decades ago. This age-related pattern makes sense evolutionarily. Throughout most of human history, older individuals served as repositories of cultural knowledge. Their value wasn't in remembering yesterday's details, but in remembering years of accumulated wisdom, skills, and knowledge that could be passed to younger generations. Sleep plays a crucial role in memory consolidation. During sleep, especially during certain sleep stages, the brain processes and strengthens memories from the day. Information in temporary storage gets transferred to more permanent storage. Connections between memories are formed and refined. This is why sleep deprivation impairs memory formation. If you don't sleep enough, memories don't consolidate properly. You might be able to hold information in mind temporarily, but it won't stick long-term. Students who stay up all night cramming for exams often discover this the hard way. Information studied without adequate sleep doesn't persist. Dreams might also play a role in memory processing, though this is still debated. Some researchers think dreams help consolidate memories by replaying and integrating them with existing knowledge. Others see dreams as more random, a byproduct of memory consolidation rather than a driver of it. There's also the phenomenon of memory reconsolidation. Each time you retrieve a memory, it becomes temporarily malleable again before being stored once more. This means that remembering something can actually change the memory. Details might be added, removed, or altered. The act of remembering is also an act of subtly rewriting. This has implications for how we think about the past. Your memories aren't fixed records of what happened. They're living constructions that evolve over time. The past you remember is partly the past that happened, and partly a creation of your present mind interpreting and reconstructing stored information. Despite these imperfections, memory remains our primary link to our personal past. It's what allows your life to be a continuous story, rather than a series of disconnected moments. Without memory, you would be trapped in an eternal present, with no history, no learning, no growth. Memory also enables meaning. We find meaning by connecting events, by seeing patterns across time, by understanding how past experiences relate to present circumstances and future possibilities. These connections are made possible by memory. As you rest here now, you might reflect on your own memories. You have a past, a history, a story. That story lives in your memory. Some parts are clear and vivid, others are hazy or forgotten, but together they form the fabric of your personal past. And just as memory connects you to the past, it also shapes your future. Your plans, hopes, and expectations are built on remembered experiences. You learn from what you've lived through. You avoid what hurt you. You seek what brought you joy. Memory guides you forward through time. In this way, memory is the thread that runs through your experience of time, connecting past, present, and future into a coherent whole. Without it, time would be fragmented, meaningless. With it, time becomes a story, your story, unfolding continuously from past to future through the ever-present now. We've explored many aspects of time in isolation, but time doesn't exist alone. Time and space are intimately connected, woven together into what physicists call space-time. Let's gently explore this deep relationship between time and space and what it reveals about the nature of reality. In everyday experience, time and space seem completely different. Space is where things are. You can move through space, forward, backward, left, right, up, down. You have freedom to move in any spatial direction. Time, on the other hand, is when things happen. You can't move through time the way you move through space. You can't go backward in time or skip forward. Time seems to flow in one direction, carrying you along whether you want to go or not. This everyday distinction between space and time is so fundamental to our experience that for thousands of years, philosophers and scientists treated them as completely separate aspects of reality. Space was the stage on which events occurred. Time was the sequence in which they occurred. They were independent dimensions. Newton's physics reinforced this separation. In Newtonian mechanics, space is absolute, a fixed, unchanging framework. Time is also absolute, a universal clock ticking at the same rate everywhere. Space and time exist independently. You can have space without time and time without space. They're fundamentally different kinds of things. But this clear separation began to break down in the 19th century. Scientists studying electricity and magnetism discovered something puzzling. The speed of light seemed to be the same for all observers, regardless of their motion. This didn't make sense if space and time were completely separate and absolute. Then came Einstein's special relativity in 1905, which we touched on earlier. Einstein showed that space and time are not independent. They're interconnected. How you measure space depends on how you're moving through time. How you measure time depends on how you're moving through space. If you're moving very fast relative to someone else, your measurements of space and time will differ from theirs. What you measure as happening at the same time, they might measure as happening at different times. What you measure as a particular distance, they might measure as a different distance. Space and time are relative, and they're mixed together in observer-dependent ways. A few years later, Einstein's mathematics teacher Hermann Minkowski showed that special relativity could be understood more simply by treating space and time as a single four-dimensional entity, space-time. Events don't happen in space at a particular time. Events happen in space-time, at particular locations in this four-dimensional continuum. In space-time, the three dimensions of space, length, width, height, and the one dimension of time, are all on equal footing. They're all dimensions of a single unified structure. Just as you can rotate your view to see different aspects of a three-dimensional object, changing your velocity gives you different views of space-time, different ways of dividing it into space and time. This is a profound shift in how we think about reality. The universe isn't a three-dimensional space evolving through time. It's a four-dimensional space-time within which all events exist at their particular locations. Your entire life, from birth to death, is a path through space-time, sometimes called your world line. Let's think about this gently. Imagine a simple space-time diagram. Draw one axis for space and one for time. Now imagine plotting your position as time passes. If you're sitting still, your world line goes straight up. You're staying at the same spatial position while moving forward in time. If you're moving through space, your world line tilts. You're changing position in space as you move through. Time. Every object, every particle has a world line in space-time. A rock sitting on the ground has a world line going straight up. Constant position in space, moving through time. A bird flying has a world line that tilts and curves, changing position as it flies, all while moving through time. Now here's something beautiful. In space-time, nothing is really moving. Motion through space is just the tilt of your world line in space-time. From a space-time perspective, your entire world line exists all at once. Your birth, your life, your death, all are positions along your world line in four-dimensional space-time. This brings us back to the block universe view we mentioned earlier. If space-time is a four-dimensional structure and all events exist at their respective locations in this structure, then past, present, and future all exist equally. They're just different regions of space-time. Your experience of time flowing is your consciousness moving along your world line, experiencing events sequentially. But there's an important difference between time and space, even in unified space-time. You can move freely in any spatial direction, but you can only move in one direction through time, forward. Your world line in space-time can tilt in various spatial directions as you move around, but it always points predominantly toward the future, never toward the past. This is related to the arrow of time we discussed earlier. The second law of thermodynamics, the increase of entropy, gives time a direction that space doesn't have. In space-time, temporal and spatial dimensions are unified, but they're not identical. Time has special properties that spatial dimensions don't have. Mathematically, this difference appears in the space-time metric, the mathematical formula that describes distances in space-time. The time dimension enters this formula with an opposite sign compared to the spatial dimensions. This opposite sign is what makes time different from space, what gives time its unique character, even within unified space-time. Einstein's general relativity, which came a decade after special relativity, deepened the connection between space and time even further. General relativity describes gravity not as a force, but as the curvature of space-time itself. Massive objects like stars and planets don't pull on other objects. Instead, they curve the space-time around them. Objects moving through this curved space-time follow curved paths, which we interpret as gravitational attraction. A planet orbiting the Sun is following the straightest possible path through the curved space-time created by the Sun's mass. This means that space and time are not just unified, they're also dynamic. Space-time can bend, warp, ripple, and stretch. Mass and energy curve space-time. The curvature of space-time influences how mass and energy move. Space, time, and matter are all interconnected in a grand cosmic dance. Gravitational waves are a beautiful example of this. When massive objects like black holes orbit each other, they create ripples in space-time itself. These ripples propagate outward at the speed of light, stretching and squeezing space and time as they pass. Gravitational waves were predicted by Einstein in 1916 and finally detected directly in 2015, a century later. The detection of gravitational waves confirmed something remarkable. Space-time is real. It's not just a mathematical abstraction. It's a physical entity that can ripple and wave. Space and time are not empty containers for matter and energy. They're part of the physical world, influenced by and influencing everything else. Near very massive or dense objects, space-time curvature becomes extreme. Near a black hole, space-time is so severely curved that not even light can escape from within a certain radius called the event horizon. Time itself behaves strangely near black holes. As we mentioned earlier, time passes more slowly in strong gravitational fields. If you could watch someone falling toward a black hole from a safe distance, you would see them slow down as they approached the event horizon. Their movements would become more and more sluggish. They would appear to freeze at the horizon, never quite crossing it from your perspective. This is because time dilation becomes infinite at the event horizon. But from the falling person's perspective, nothing special happens at the event horizon. Time passes normally for them. They cross the horizon and continue falling toward the center. The difference is entirely about perspective, about how space-time is measured from different locations in the gravitational field. This reveals something profound. There's no absolute frame of reference in the universe, no privileged perspective from which to measure space and time. Every observer has their own equally valid measurements. Space-time itself is all that's truly real, with different observers carving it up into space and time in different ways. The unification of space and time also has implications for causality. In space-time, events are connected by what are called light cones. From any event, there's a cone of future events that could be causally influenced by it. Events that light from the original event could reach. There's also a cone of past events that could have causally influenced it, events whose light could have reached it. Events outside these light cones, too far away in space and too close in time for light to travel between them, cannot causally influence each other. They're space-like separated. Events within the light cones are time-like separated and can have causal connections. This structure of light cones in space-time determines what can influence what can cause what. It's the causal structure of the universe, built into the geometry of space-time itself. Causes can only propagate within the light cone, never faster than light, never outside the cone. This also means that nothing can travel faster than light. If you could send a signal faster than light, you could send it outside your light cone. But relativity shows that for different observers, such a signal would be traveling backward in time from some perspectives. Faster than light travel would allow time travel to the past, which creates logical paradoxes. The structure of space-time itself seems to prevent this. The cosmic speed limit, the speed of light, is not arbitrary. It's woven into the structure of space-time. Light travels at the speed it does because that's the speed of causality, the speed at which cause and effect can propagate through space-time. Anything without mass, including light itself, travels at this speed. Anything with mass travels slower. Space and time are also expanding together. When we say the universe is expanding, we don't mean things are flying apart through a pre-existing space. We mean space-time itself is stretching. The distances between galaxies are increasing because space is growing. This expansion affects time too. In the early universe, when everything was much closer together, time itself was different in certain ways. The rate of processes, the frequencies of light, everything was affected by the different scale of space-time. Looking at distant galaxies, we're looking back in time because light takes time to travel. The farther away something is, the older the light we're seeing. The most distant observable objects show us the universe as it was billions of years ago, when space-time itself was younger and smaller. This means that space and time are not just connected, they have a history together. Space-time itself evolves. It began small and dense at the Big Bang and has been expanding ever since. The arrow of time we experience is connected to this cosmic expansion, to this evolution of space-time itself. As you rest here quietly, you exist at a particular location in space-time. Not just a place in space, but a place in four-dimensional space-time. Your world line stretches from your birth to this present moment and continues into your future. All around you, the world lines of other people, other objects, other particles, trace their paths through space-time. Space and time together form the fabric of reality. They're not separate things, but aspects of a unified whole. This unity is one of the most beautiful discoveries of modern physics. It reveals that the universe has an elegant mathematical structure, that space and time are intimately related at the deepest level. Understanding this doesn't change your everyday experience. You still experience space and time as different. You still move through space and are carried through time. But knowing that underneath this experience is a unified space-time adds a layer of depth to your understanding of reality. You are a four-dimensional being in a four-dimensional universe. Your existence is not just here, but here now, a location in space-time. The cosmos is not just a vast space, but a vast space-time, a four-dimensional arena within which all of existence plays out. One of the most basic aspects of our experience is the feeling that time flows. Time passes, moments come and go. The future becomes the present, and the present becomes the past. This flow of time seems as real as anything we experience. And yet, when we examine time carefully through the lens of physics and philosophy, this flowing quality becomes mysterious and problematic. Let's think about this gently. What does it mean to say that time flows? Flow is itself a temporal concept. Rivers flow. They move through space over time. Traffic flows. Vehicles move along roads as time passes. But time flowing would mean time is moving through. What? Time? The concept seems circular. Strange. When we say a river flows, we mean its position changes over time. The water that was here a moment ago is now downstream. But what does it mean for time itself to change position? Time can't move through time. That doesn't make logical sense. And yet, the feeling persists. Time seems to flow. The present moment seems to move forward like a spotlight sweeping across a stage, illuminating one moment after another. What was future becomes present, then quickly recedes into the past. This sensation of temporal passage is fundamental to how we experience reality. Philosophers have wrestled with this puzzle for centuries. Some argue that the flow of time is real, but simply difficult to describe, because our language isn't equipped to talk about something so fundamental. Others argue that the flow of time is an illusion, a product of how our consciousness works, rather than a feature of time itself. Let's consider the second view more carefully. If time doesn't actually flow, why does it seem like it does? One possibility is that the feeling of flow comes from our consciousness experiencing moments sequentially. We experience one moment, then another, then another. This sequential experience creates the sensation that time is passing, that we're moving through time. Think about watching a movie. The film itself is static. All the frames exist simultaneously on the disc or in the file. But when you watch the movie, you experience it as flowing, as moving, as unfolding. One scene follows another in sequence. This is because your consciousness processes the frames one after another. The flow you experience is created by how you're accessing the information, not by any actual movement in the film itself. Perhaps time is similar. Perhaps all moments exist in space-time as we discussed earlier. The flow we experience is created by our consciousness moving along our world line, experiencing events sequentially. The movement is not in time itself, but in our experience of time. This view aligns with the block universe perspective from physics. In space-time, all events exist at their respective locations. There's no objective present moment sweeping through space-time, making moments real one by one. All moments are equally real, laid out in four-dimensional space-time. Our experience of flowing time is our consciousness tracing its path through this timeless structure. But this raises questions. If all moments exist equally in space-time, why do we experience them in sequence? Why does consciousness move along the world line rather than experiencing all moments simultaneously? We don't have complete answers to these questions. Consciousness itself remains mysterious, and its relationship to time is part of that mystery. There's also the puzzle of why we remember the past, but not the future. If all moments exist equally in space-time, why is there an asymmetry in our knowledge? We have records, memories, and evidence of past events, but we don't have records or memories of future events. This asymmetry seems connected to the arrow of time, to entropy increasing toward the future. Records and memories are low-entropy structures. that get created as a result of past events. They're traces left behind by the past. The future doesn't leave traces in the present because causality works from past to future, not the reverse. So even if time doesn't flow in some objective sense, there's still an asymmetry between past and future built into the structure of the universe. This asymmetry shapes our experience and creates what feels like a flow from past toward future. Some philosophers distinguish between two kinds of time, A-series time and B-series time. These terms come from philosopher J.M.E. McTaggart's early 20th century analysis of time. A-series time is time as we experience it, with genuine passage. Events are future, then become present, then become past. The present moment is special, real in a way that past and future are not. Time flows, and this flow is an objective feature of reality. B-series time is time as physics describes it, with events ordered in a sequence but no genuine flow. Events are earlier or later than each other, but there's no moving present moment. All events simply exist at their respective positions in time, just as all places exist at their respective positions in space. McTaggart argued that A-series time involves a logical contradiction and therefore can't be real. If an event is first future, then present, then past, it has contradictory properties. How can the same event be both future and past? His conclusion was that time itself is unreal, a radical claim. Most philosophers haven't followed McTaggart into denying time's reality altogether, but his analysis highlighted the tension between our experience of flowing time, A-series, and the static picture of time in physics, B-series. Modern physics leans toward B-series time. Relativity treats space-time as a four-dimensional structure without any objective flow. Quantum mechanics, our best theory of the microscopic world, also describes time without any flow, just probabilities of different outcomes at different times. Yet our experience is firmly A-series. We experience flow, change, becoming. The present moment feels special, different from past and future. This creates a profound puzzle: how to reconcile our experience with what physics tells us about reality. One possibility is that flow is emergent. Perhaps at the fundamental level described by physics, there is no flow, just events at different positions in space-time. But at higher levels of organization, the level of conscious beings with memories and anticipations, something that looks and feels like flow emerges. This would be similar to how temperature emerges from molecular motion. At the fundamental level, there are just particles moving. Temperature isn't a property of individual particles, but when you have many particles together, temperature emerges as a statistical property of the system. Perhaps temporal flow similarly emerges from the way complex systems like conscious beings interact with space-time. Another possibility involves consciousness more directly. Perhaps consciousness doesn't just passively experience time. Perhaps it plays an active role in creating the flow. Some interpretations of quantum mechanics suggest that consciousness might be involved in collapsing quantum possibilities into actualities. If so, perhaps the flow of time is connected to this process of actualization. These are speculative ideas at the edge of our current understanding. The relationship between consciousness and time remains one of the deepest mysteries in science and philosophy. Let's consider another aspect of this puzzle: the present moment. If time doesn't flow, if all moments exist equally, why do we experience one particular moment as now? Why this moment rather than some other moment? This is sometimes called the problem of the privileged present. From the block universe view, every moment has equal claim to being now. Every moment along your world line involves you experiencing that moment as now. So in one sense, every moment is now, but only to the you experiencing that particular moment. There isn't one universal now shared by everyone, as relativity showed us, but for each observer at each moment, there's a subjective now, the moment they're experiencing. This now isn't objectively special. It's just the moment that particular observer at that time is experiencing. Think of it like this. Every point on a path could be described as here by someone standing at that point. Here isn't an objective property of locations, it's a relation between a location and an observer. Similarly, now might not be an objective property of moments, but a relation between a moment and a consciousness experiencing it. This suggests that the flow of time might be perspectival, dependent on the perspective of the experiencer, rather than an objective feature of time itself. Just as here depends on where you are, now depends on when you are in space-time. But even if flow is perspectival, rather than objective, it's still real to us. Our experience of time flowing is as real as any experience we have. Even if it's not how time is at the deepest physical level, it's how time is for us, at the level of conscious experience. Perhaps the question, does time really flow, is asking the wrong thing. Perhaps both perspectives are valid. Time doesn't flow at the fundamental physical level, but it does flow at the experiential level. Both descriptions are true in their respective domains. This might sound like a compromise, but it's actually a recognition that reality has different descriptions at different levels. Water, at the molecular level, is H2O molecules in motion. Water, at the experiential level, is wet, flows, and quenches thirst. Both descriptions are valid. They're describing the same thing from different perspectives. Similarly, time at the physical level might be a dimension of space-time, static, and unchanging. Time at the experiential level flows, passes, moves from future through present to past. Both could be valid descriptions of the same reality from different perspectives. What's clear is that our experience of temporal flow is intimately connected to consciousness, memory, and anticipation. Without consciousness, it's unclear whether the concept of flow would even make sense. Flow might require an experiencer to flow past, a consciousness to experience the succession of moments. This gives consciousness a special relationship to time. Perhaps consciousness doesn't just exist in time, perhaps it creates, or at least participates in creating, the flowing quality of time. This is a deep and unresolved question. As you rest here now, notice your experience of time. Does time feel like it's flowing? Can you sense the present moment moving forward? Or does it feel more static, with your awareness simply existing in this moment? There's no right answer, just your experience, whatever it may be. The flow of time might be the most immediate and undeniable aspect of your experience, or it might fade into the background, barely noticeable. Either way, you're experiencing time from the inside, as a conscious being embedded in space-time, with memory of the past and anticipation of the future. Whether time truly flows in some objective sense remains an open question, but your experience of flow is real. And in the end, perhaps that's what matters most. You live in time, experience time, are shaped by time. Whether the flow is fundamental or emergent, objective or perspectival, it's real for you. And that reality is profound. We've explored time in relativity, where it's woven together with space into space-time. Now let's turn our attention to time in quantum mechanics, the physics of the very small, the realm of atoms and particles. Here time takes on yet another character, revealing new mysteries about its nature. Quantum mechanics is the most successful scientific theory ever developed. It describes the behavior of particles, atoms, and molecules with extraordinary precision. Every electronic device you use, every chemical reaction in your body, every interaction of light with matter, all of these follow quantum mechanical rules. And yet, quantum mechanics is deeply strange. It describes a world that seems utterly alien to our everyday experience. Particles can be in multiple places at once. They can pass through barriers they shouldn't be able to penetrate. They can be connected across vast distances in ways that seem to defy locality. And their behavior involves fundamental randomness that can't be predicted, only described probabilistically. Time in quantum mechanics is strange too, though in different ways than in relativity. In quantum mechanics, time plays a special role, a role that's different from the role of space. This is curious because relativity tells us that space and time should be treated on equal footing. In quantum mechanics, they're not. Let's think about this gently. In quantum mechanics, the state of a system is described by something called a wave function. This wave function contains all the information about the system, where particles might be, what momenta they might have, and so on. The wave function doesn't tell you where a particle is exactly. Instead, it gives you probabilities for where you might find it if you look. This wave function evolves over time according to an equation called the Schrödinger equation. Given the wave function at one time, the Schrödinger equation tells you what it will be at any later time. The evolution is smooth, continuous, and deterministic. If you know the wave function now, you can predict it perfectly at any future time. This sounds reassuring. There's still determinism in quantum mechanics, at least for the wave function. But here's where things get strange. When you actually measure a quantum system, when you observe where a particle is or what its momentum is, the wave function doesn't smoothly evolve. Instead, it suddenly collapses to one of the possible outcomes. Before measurement, the wave function might describe a particle as being in many places at once, a superposition of possibilities. After measurement, you find the particle in one specific place, and the wave function instantly becomes concentrated at that location. This collapse is discontinuous, sudden, and seems to involve genuine randomness. The Schrödinger equation can't describe this collapse. The equation only describes the smooth evolution between measurements. The collapse is something else, something outside the normal time evolution of quantum mechanics. This is sometimes called the measurement problem, and it's one of the deepest puzzles in quantum mechanics. Time enters this puzzle in interesting ways. During the smooth evolution described by the Schrödinger equation, time is treated as a fixed parameter, a background against which quantum states evolve. Time is not itself a quantum variable. You don't have uncertainty in time the way you have uncertainty in position or momentum. This is different from how quantum mechanics treats space. Position is a quantum observable, something that can be uncertain, that can exist in superposition. But time is not an observable in standard quantum mechanics. It's a classical parameter, external to the quantum system. Why this asymmetry between space and time? It's a puzzle that has troubled physicists for decades. Relativity says space and time should be on equal footing. Quantum mechanics treats them very differently. Reconciling these two pillars of modern physics, quantum mechanics and relativity, remains one of the great challenges of theoretical physics. There's another temporal puzzle in quantum mechanics, the arrow of time. We've discussed how the second law of thermodynamics gives time a direction. Entropy increases toward the future. But the Schrödinger equation is time reversible. If you run a quantum evolution backward in time, you get a perfectly valid quantum evolution. The equation doesn't distinguish between past and future. So where does the arrow of time come from in quantum mechanics? How does the time-reversible Schrödinger equation lead to the irreversible increase of entropy we observe? Part of the answer involves measurement and collapse. When a quantum system is measured and the wave function collapses, this collapse seems to be irreversible. You can't uncollapse a wave function. Once you've measured where a particle is, you can't unmeasure it and restore the previous superposition of possibilities. But this just pushes the question back. Why is measurement irreversible? What makes it different from the reversible evolution described by the Schrödinger equation? These questions connect to the measurement problem and remain controversial. Another quantum phenomenon with interesting temporal implications is entanglement. When two particles are entangled, their quantum states are connected in deep ways. Measuring one particle instantly affects the quantum state of the other, even if they're far apart in space. Einstein called this spooky action at a distance and found it troubling. Entanglement doesn't violate relativity's speed of light limit because you can't use it to send information faster than light, but it does create correlations between distant measurements that seem to transcend space. Some physicists have wondered whether entanglement might also transcend time, whether measurements could be correlated not just across space but across time. There's evidence that something like this is possible. In certain experiments, particles can be entangled across time as well as space. A measurement made now can be correlated with a measurement made later in ways that seem to involve quantum connections across time. This temporal entanglement is real and has been demonstrated experimentally. What this means for our understanding of time is still unclear. It suggests that quantum mechanics creates connections through time that are as fundamental as connections through space. The quantum realm doesn't respect our usual distinctions between past, present, and future in quite the way classical physics does. Let's consider another quantum temporal puzzle, the quantum Zeno effect. This phenomenon is named after Zeno's paradoxes from ancient Greek philosophy. In quantum mechanics, if you measure a system repeatedly and rapidly, you can actually prevent it from evolving. Here's a simple example. Imagine a particle that would naturally transition from one state to another over time. If you measure it frequently to see if it has transitioned yet, the very act of measuring can freeze the transition. The particle stays in its initial state because you keep collapsing the wave function back to that state before the transition can complete. This means that measurement, observation, can affect the temporal evolution of quantum systems. Time evolution in quantum mechanics is not entirely independent of whether and how often you look at the system. This is deeply counterintuitive and raises questions about the relationship between consciousness, observation, and time. Some interpretations of quantum mechanics take these puzzles in radical directions. The many worlds interpretation, for example, suggests that every quantum measurement doesn't actually collapse the wave function. Instead, the universe splits into multiple branches, one for each possible outcome. Each branch experiences one outcome, but all branches are equally real. In this interpretation, time becomes even stranger. Every moment, the universe branches countless times. Your timeline is just one path through an ever-branching tree of possibilities. Other versions of you exist in other branches, experiencing different outcomes. If many worlds is correct, the flow of time involves continuous branching. The future is not a single path, but an ever-expanding array of possibilities, all of which become real. Your experience is of following one particular branch, but the branch structure itself is the full reality of time. Other interpretations avoid multiple worlds, but face their own temporal puzzles. In some versions, the wave function collapse is objective, something that happens in reality, not just in our knowledge. But what causes this collapse, and when exactly does it occur? Different proposals give different answers, each with its own implications for time. There are also proposals for quantum theories of time itself. Perhaps at the smallest scales, the Planck scale, about 10 raised to 35 meters and 10 raised to 43 seconds, time becomes granular rather than continuous. Perhaps time is made of discrete moments, quantum time atoms, rather than flowing smoothly. If time is quantized, there would be a shortest possible time interval, a fundamental tick of the cosmic clock. Below this scale, the concept of duration might lose meaning. Time would be fundamentally discrete, like frames in a movie rather than a continuous flow. This is highly speculative, but it emerges naturally from attempts to combine quantum mechanics with general relativity. In quantum gravity theories, still under development, space-time itself becomes a quantum entity, subject to quantum fluctuations and uncertainties. Time at this level might be as fuzzy and uncertain as position and momentum are in standard quantum mechanics. Another quantum temporal phenomenon worth mentioning is quantum tunneling. Particles can pass through barriers that classical physics says they shouldn't be able to cross. A particle without enough energy to climb over a hill can sometimes appear on the other side anyway, as if it tunneled through. How long does this tunneling take? This question has puzzled physicists. Some calculations suggest tunneling is instantaneous, which would seem to violate relativity. Other analyses suggest it takes a finite time, but measuring this time precisely is extremely difficult. The question of tunneling time remains contentious. These quantum temporal puzzles reveal something important. Our understanding of time is still incomplete. We have relativity, which describes time at large scales with space, gravity, and cosmic expansion. We have quantum mechanics, which describes the behavior of particles and atoms, but we don't yet have a complete theory that unifies these descriptions. When we try to combine quantum mechanics and general relativity to create a theory of quantum gravity, we encounter deep conceptual problems. Time in relativity is part of dynamic spacetime. Time in quantum mechanics is an external parameter. How do we reconcile these different treatments? This is one of the great unsolved problems in physics. Until we solve it, our understanding of time at the most fundamental level remains incomplete. We don't fully know what time is at the deepest level of reality, where quantum effects and gravitational effects both become important. As you rest here, the atoms in your body are following quantum mechanical laws. Electrons orbit nuclei in probability clouds rather than definite paths. Quantum tunneling occurs constantly in the chemistry of your cells. You are, at the microscopic level, a quantum system, yet your experience of time is classical, not quantum. You don't experience superpositions of moments or wave function collapses. You experience a smooth flow of time, one moment following another. Somehow, the strange quantum world at small scales gives rise to the familiar classical world at larger scales. This emergence of classical from quantum is another deep puzzle, related to the measurement problem. How does the weird quantum realm produce the ordinary world we experience? And what role does time play in this transition? We don't have complete answers, but we can appreciate the mystery, the fact that time at the quantum level is stranger than we ever imagined. The comfortable classical time of our experience sits atop a quantum foundation that defies easy understanding. Time in quantum mechanics is both familiar and alien. It flows forward in equations, yet measurement seems to interrupt that flow. It's treated as a background parameter, yet quantum effects create temporal correlations and entanglements. It's continuous in our theories, yet might be discrete at the deepest level. These mysteries remind us that time is deeper and more complex than our intuitions suggest. Every answer we find raises new questions. Every layer we peel back reveals another layer. Beneath, time, it seems, will continue surprising us for a long time to come. Time travel has captivated human imagination for over a century. Stories of traveling to the past or future fill our books and movies. But is time travel actually possible? What does physics tell us about the possibility of moving through time in ways other than the ordinary forward march at 1 second per second? Let's explore this fascinating question gently and carefully. First, let's clarify something important. We're all time travelers already. You're traveling through time right now, moving from the past toward the future at a steady rate. Every moment that passes, you've traveled 1 second further into the future. In this sense, time travel to the future is not only possible, it's inevitable. You can't stop doing it. But of course, when we talk about time travel, we usually mean something more dramatic. We mean traveling to the future faster than normal, or traveling to the past, or jumping across time rather than moving through it continuously. These more exotic forms of time travel are what we'll explore. Let's start with traveling to the future faster than normal. Surprisingly, this is not only possible, it's been done. Einstein's theory of relativity tells us that time passes at different rates, depending on how fast you're moving and how strong the gravitational field is around you. If you travel at very high speeds, time passes more slowly for you than for people who are stationary. This is time dilation, which we discussed earlier. From your perspective, time passes normally. But when you return from your high-speed journey, you find that more time has passed for everyone else. You've effectively traveled to their future. This isn't science fiction. It's established physics, confirmed by many experiments. Astronauts on the International Space Station age slightly more slowly than people on Earth because they're moving at high speed and in a weaker gravitational field. The difference is tiny, only a few milliseconds over months in space, but it's real and measurable. If we could build a spacecraft that travels at speeds close to the speed of light, time dilation would become dramatic. Imagine a spacecraft traveling at 99.5% of the speed of light. If you spent 1 year on this spacecraft and then returned to Earth, about 10 years would have passed on Earth. You would have traveled 9 years into Earth's future, while experiencing only 1 year of time yourself. At even higher speeds, the effect becomes more extreme. At 99.99% of the speed of light, 1 year for you would equal about 70 years on Earth. You could, in principle, travel thousands of years into Earth's future, while aging only a few years yourself. This kind of time travel to the future is perfectly consistent with known physics. The only limitation is technological. We don't have any way to accelerate a spacecraft to such enormous speeds. But there's no law of physics that forbids it. It's theoretically possible. Gravitational time dilation offers another route to the future. If you spent time near a very massive object, like a black hole, time would pass more slowly for you than for people far away. The movie Interstellar depicted this. Characters spend a few hours on a planet near a black hole, and when they return to their ship, decades have passed for their colleague who remained farther away. This scenario is scientifically accurate. Near the event horizon of a massive black hole, time dilation becomes extreme. You could orbit close to a black hole for what feels like a few hours, then travel back out to find that centuries have passed in the wider universe. You would have traveled to the future. Again, the only limitation is practical. Getting near a black hole safely, then escaping again, would require technologies far beyond our current capabilities. But the physics is sound. This kind of time travel to the future is possible according to general relativity. So traveling to the future is not only possible, there are 2 known methods for doing it, both confirmed by physics. Time travel to the future is real, though currently impractical at dramatic scales. But what about traveling to the past? This is where things get much more complicated and controversial. Can you travel backward in time? Can you visit yesterday or last year, or ancient Rome? Einstein's equations of general relativity allow for some very strange space-time geometries. Some solutions to these equations include what are called closed time-like curves, paths through space-time that loop back on themselves in time. If you followed one of these curves, you could potentially return to an earlier time. The most famous example is the Gödel universe, named after mathematician Kurt Gödel. Gödel found a solution to Einstein's equations describing a rotating universe in which closed time-like curves exist everywhere. In such a universe, you could travel in a circle through space and arrive back at your starting point at an earlier time. There's also the theoretical possibility of wormholes, tunnels through space-time connecting different regions. If a wormhole connected 2 different times as well as 2 different places, you might be able to enter it at one time and exit at an earlier time, effectively traveling to the past. Another theoretical possibility involves cosmic strings, hypothetical defects in space-time left over from the early universe. If 2 cosmic strings passed each other at very high speeds, they might create closed time-like curves in their vicinity, allowing time travel to the past. These are all genuine solutions to Einstein's equations. They're mathematically valid, but do they represent physically possible situations? This is where physicists disagree. The main problem with backward time travel is causality. If you could travel to the past, you could potentially change events that led to your present. You could create paradoxes. The most famous is the grandfather paradox. If you traveled to the past and prevented your grandfather from meeting your grandmother, you would never be born. But if you were never born, you couldn't travel to the past to prevent their meeting. It's a logical contradiction. There are various proposed resolutions to these paradoxes. One is the self-consistency principle. Maybe the universe simply doesn't allow paradoxes to occur. If you try to prevent your grandparents from meeting, something will always prevent you from succeeding. Events conspire to maintain consistency. This might sound contrived, but it's not logically impossible. The idea is that space-time, if it allows time loops, must be self-consistent. Events in the loop must be arranged so they don't contradict each other. You could interact with the past, but only in ways that lead to the present you came from. Another proposed resolution involves parallel timelines or alternate worlds. When you travel to the past, maybe you create or enter a different timeline. Changes you make affect that timeline, but not the one you came from. This avoids paradoxes because your original timeline remains unchanged. This idea connects to the many worlds interpretation of quantum mechanics we mentioned earlier. If the universe branches at every quantum event, maybe time travel simply takes you to a different branch. You can affect the past of that branch without affecting your own history. A more conservative position is that backward time travel is simply impossible. Despite the mathematical solutions that seem to allow it, perhaps nature has some mechanism that prevents closed time-like curves from ever actually forming. Physicist Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics prevent time travel to the past. One reason to think chronology is protected involves quantum effects. When physicists try to analyze what would happen at a point where a closed time-like curve forms, quantum fluctuations seem to become infinite. The energy density might become so large that it creates a singularity, a breakdown of space-time, that prevents the time machine from ever functioning. This suggests that even though general relativity allows certain time travel solutions, quantum effects might prevent them from being physically realized. To know for sure, we would need a complete theory of quantum gravity, which we don't yet have. Another issue is that all the known time travel solutions in general relativity require exotic conditions. The Gödel universe requires the entire universe to be rotating, which observations show our universe isn't. Traversable wormholes, if they could exist, would require exotic matter with negative energy density to hold them open. Cosmic strings, if they exist at all, are incredibly rare. None of these scenarios are things we could create with any foreseeable technology. Even if backward time travel is possible in principle, it might be forever beyond practical reach. There's also a curious argument against backward time travel based on the absence of time travelers from the future. If time travel to the past ever becomes possible, even millions of years in the future, why haven't we been visited by time travelers from that future? Where are they? One response is that maybe they're here but hiding, or we don't recognize them. Another is that maybe civilizations that develop time travel also develop rules about not interfering with the past, or maybe time travel is possible but only to times after the first time machine is built. You can't travel to before time machines existed. Or maybe the simplest answer is correct. Backward time travel is impossible, which is why we've never seen time travelers from the future. As you rest here now, you might imagine what it would be like to visit the past or future. Would you want to? What would you do? These questions have fascinated storytellers and philosophers because time travel, even if impossible, helps us think about the nature of time, causality, and existence. The fact that we can even ask these questions seriously, using real physics to analyze them, is remarkable. A century ago, time travel was pure fantasy. Now we know that traveling to the future is definitely possible, even if impractical at dramatic scales. And traveling to the past remains an open question, neither definitively allowed nor definitively forbidden by known physics. What's clear is that time is more flexible than our ancestors imagined. It's not an absolute, unchanging flow. It bends, stretches, and interacts with space and matter in complex ways. Whether this flexibility extends to allowing closed loops in time, travel to the past, remains one of the great mysteries. Perhaps future generations will know the answer. Perhaps they'll develop technologies or theories that reveal whether backward time travel is truly possible. Or perhaps we already know the answer in the negative, simply by the absence of any confirmed visitors from the future. Either way, the question itself reveals how far our understanding has come. We can analyze time travel using sophisticated physics and mathematics. We can identify what would be required and what problems would arise. Even if we never build a time machine, the exercise of thinking about it has deepened our understanding of time itself, and that understanding continues to grow. Every generation learns more about time's nature, discovers new aspects of its behavior, pushes the boundaries of what seems possible. Time, it seems, still has secrets to reveal. Throughout our exploration, we've touched repeatedly on consciousness and its relationship to time. Now let's settle into this connection more deeply. Consciousness and time are intimately intertwined in ways that are profound and mysterious. To be conscious is, in many ways, to experience time. Think about what consciousness is like from the inside. You have thoughts, feelings, perceptions, but these don't exist as isolated, frozen moments. They flow. One thought leads to another. Perceptions change continuously. Feelings arise, persist, and fade. The very nature of conscious experience seems to be temporal, happening in time, unfolding through time. Could you be conscious without time? Could consciousness exist in a single frozen instant? These questions are difficult to even formulate clearly, which suggests how fundamental time is to consciousness. To be aware seems to require duration, sequence, change. Consciousness appears to be inherently temporal. One of the most basic features of consciousness is its stream-like quality. William James, the pioneering psychologist, called this the stream of consciousness. Your experience doesn't come in discrete, separate chunks. It flows continuously, one moment blending into the next. There are no sharp boundaries between successive moments of consciousness. This flowing quality of consciousness mirrors our experience of time flowing. Perhaps they're connected. Perhaps the flow of time we experience is actually the flow of consciousness itself. Maybe time feels like it flows because consciousness flows, and consciousness is our window onto time. But consciousness doesn't just flow, it also unifies experiences across time. Right now, as you listen to these words, you're experiencing them as connected, as forming sentences with meaning. To understand a sentence, you need to hold its beginning in mind while hearing its end. Your consciousness spans a brief duration, creating unity across successive moments. This is sometimes called the specious present or the psychological present, as we mentioned earlier. It's the span of time that feels immediately present to consciousness, typically somewhere between half a second and a few seconds. Within this span, events feel simultaneous, part of one extended now. This psychological present is constructed by your brain. Neural processes bind together information arriving at slightly different times, creating the experience of a unified moment. When you see someone speaking, the sight of their lips moving and the sound of their words arrive at different times, processed by different brain regions at different speeds, yet you experience them as synchronized, as happening together. This temporal binding is remarkable. Your brain is constantly solving timing problems, aligning inputs, creating coherence across time. The result is your seamless conscious experience, where everything feels properly synchronized and connected. Memory, as we explored earlier, also binds consciousness across longer time spans. Your memories connect your present consciousness to past moments of consciousness. They create continuity of identity across time. You feel like the same person you were yesterday, or 10 years ago, because memory links these temporally distant states of consciousness. Without memory, each moment of consciousness would be isolated, disconnected. You would have no sense of personal history, no narrative of your life. Memory creates temporal depth in consciousness, giving you a past that extends beyond the immediate present. Similarly, imagination and anticipation extend consciousness into the future. You can mentally project yourself forward, imagining future scenarios, planning actions, anticipating outcomes. This future-directed aspect of consciousness is as important as memory's backward reach. Together, memory and anticipation give consciousness a temporal structure. You exist not just in a narrow present, but with awareness of past and future. Your consciousness has temporal depth, temporal extension. You're aware of time stretching behind and ahead of you. This temporal structure of consciousness shapes how we experience time's passage. When consciousness is filled with activity, thoughts, perceptions, feelings flowing rapidly, time seems to pass quickly. When consciousness is relatively empty, waiting, bored, with little happening, time seems to drag. This suggests that our perception of time's rate depends partly on the density of conscious content. More happening in consciousness correlates with faster subjective time. Less happening correlates with slower subjective time. Time perception is thus intimately tied to the dynamics of consciousness itself. There's also the question of whether consciousness is necessary for time to exist. Would time exist in a universe without any conscious beings? Most physicists would say yes. Space-time is a physical structure that doesn't require observers. Time would exist whether anyone was there to experience it or not. But some philosophers and physicists have proposed that consciousness might play a more fundamental role. Perhaps the flow of time, the distinction between past and future, the reality of the present moment. Perhaps these features require consciousness. Perhaps time without consciousness would be like the block universe, a static four-dimensional structure with no flow, no privileged present. This is a controversial idea. It suggests that consciousness isn't just experiencing time, but somehow participating in creating time's experiential qualities. Without consciousness, there might be temporal ordering, events at different coordinates in space-time, but no flow, no passage, no lived time. Another fascinating connection between consciousness and time involves the sense of duration. How does consciousness estimate how much time has passed? This ability, called time perception, is something we do constantly but rarely think about. Research shows that time perception involves multiple brain systems. Some track short intervals using neural oscillations, rhythmic patterns of brain activity that act like internal clocks. Others estimate longer durations based on memory encoding and attention. The more attention you pay and the more memories you form, the longer a period feels in retrospect. Interestingly, time perception can be altered by various factors. Drugs that affect brain chemistry can speed up or slow down perceived time. Brain damage to certain regions can impair time perception. Even mood affects it. Depression often makes time feel slow and heavy, while mania can make it feel rushed and compressed. This malleability of time perception suggests that our experience of duration is actively constructed by the brain. There's no single time perception center that directly reads objective time. Instead, various brain processes contribute to creating your sense of how much time has passed, and this constructed sense can vary significantly from clock time. Meditation and contemplative practices often involve altered time perception. Experienced meditators sometimes report that time seems to expand or become less relevant during deep meditation. The usual sense of time passing can fade, replaced by a sense of timeless presence. Some meditation traditions distinguish between different modes of temporal consciousness. The ordinary mode is characterized by constant mental movement, thoughts about past and future, desires and regrets, plans and memories. This mode creates a strong sense of time passing, of being in time. The meditative mode involves settling into present moment awareness without mental elaboration. In this mode, the sense of time passing can diminish. The present moment becomes more spacious, less confined. This doesn't mean time stops, but the psychological experience of time changes dramatically. These altered states suggest that our normal temporal consciousness is just one possibility. Consciousness can relate to time in different ways. The rushing, time-bound quality of ordinary consciousness is not inevitable. It's one mode of temporal awareness among others. There's also the mysterious connection between consciousness and the now. Why do you experience this particular moment as present? As we discussed earlier, from a block universe perspective, every moment along your world line involves you experiencing that moment as now. But phenomenologically, subjectively, there's only one now, this one, the moment you're experiencing right now. This now is where consciousness exists. You can remember past moments and anticipate future ones, but you can only be conscious now. Consciousness seems tied to the present moment in a fundamental way. It's always now in consciousness, even though which now keeps changing. Some philosophers argue that consciousness itself creates the present moment. Without consciousness, there might be no meaningful distinction between now and other times. The present might be a feature of conscious experience rather than an objective feature of time itself. This is related to the hard problem of consciousness, the question of why subjective experience exists at all. Why does it feel like something to be conscious? Why is there an inner, experiential quality to certain physical processes? These questions remain deeply puzzling. Similarly puzzling is why consciousness is always experienced as now. Why doesn't consciousness have access to multiple times simultaneously? Why is it confined to a moving present? We don't have complete answers, but these questions suggest deep connections between consciousness and temporality. Another aspect worth considering is how consciousness gives meaning to time. Physical time, as described by physics, is neutral, just coordinates in space-time. But conscious experience of time is rich with meaning. Some moments feel significant, precious, memorable. Others feel empty, wasted, forgettable. This meaningful quality of experienced time comes from consciousness. We care about time because we're conscious beings with projects, relationships, experiences that matter to us. Time is not just a dimension to be measured, but a medium of life, and consciousness makes it so. The finitude of time also becomes meaningful through consciousness. We're aware that we have limited time. This awareness shapes how we live, what we value, how we choose to spend our days. Consciousness of mortality, awareness that time will end for us, profoundly influences human life and culture. Animals presumably experience time in some way, but likely without the elaborate temporal consciousness humans possess. They probably don't worry about the future the way we do, or reflect on the past, or contemplate their own mortality. Human consciousness has a unique temporal character. As you rest here now, you can notice your own temporal consciousness. Thoughts arising and passing, breath flowing in and out, sounds appearing and fading. All of this happens in your consciousness, and all of it has temporal structure. You are experiencing time from the inside, as it feels to be a conscious being embedded in time. This inner perspective on time is irreducible. You can study time scientifically, measure it precisely, describe it mathematically, but none of that captures what it's like to experience time consciously. The felt quality of duration, the sense of flow, the immediacy of the present. These are features of conscious experience that no objective description fully captures. And yet, consciousness is somehow generated by physical processes in your brain, processes that themselves unfold in time according to physical laws. How unconscious physical processes give rise to conscious experience, including temporal experience, remains one of the deepest mysteries in science and philosophy. Perhaps consciousness and time are more deeply connected than we yet understand. Perhaps solving the mystery of consciousness will also illuminate the mystery of time, and vice versa. For now, we can simply appreciate the profound connection between them, how consciousness gives us access to time, and how time gives structure to consciousness. We've explored time's beginning in the Big Bang. Now, as we near the end of our journey together, let's contemplate time's possible end. Will time go on forever? Or might time itself come to an end? What does the far future hold for time and the universe? These are questions about the ultimate fate of everything. They're grand and cosmic in scope, yet they connect to how we think about time's nature. If time had a beginning, might it also have an end? Let's explore these possibilities gently, without urgency, letting the vastness of cosmic time wash over us calmly. The fate of time is intimately connected to the fate of the universe. Time, as we've seen, is part of space-time, woven together with space. What happens to the universe happens in some sense to time as well. So to understand time's possible future, we need to consider the universe's future. Current observations tell us that the universe is expanding. Galaxies are moving apart from each other, as space itself stretches. For decades, scientists assumed this expansion would gradually slow down due to gravity. The matter in the universe should attract other matter, resisting the expansion. The question was whether there was enough matter to eventually stop and reverse the expansion, causing the universe to collapse back on itself in a big crunch, or whether the expansion would continue forever, gradually slowing, but never quite stopping. Then, in the late 1990s, astronomers made a shocking discovery. The expansion of the universe isn't slowing down, it's speeding up. Something is causing the universe to expand faster and faster. Scientists call this mysterious something dark energy. We don't really understand what dark energy is. It appears to be a property of space itself, a kind of inherent energy that causes space to expand. The more space exists, the more dark energy there is, causing even more expansion. It's a runaway process. If dark energy continues to dominate the universe's evolution, and current evidence suggests it will, then the universe will expand forever at an accelerating rate. Galaxies will move farther and farther apart. Eventually, they'll be so distant that light from one can never reach another. Each galaxy will become isolated, alone in an ever-expanding void. This scenario is sometimes called the Big Freeze or heat death. Over vast spans of time, trillions and trillions of years, stars will burn out. New stars will stop forming as gas becomes too dispersed. Galaxies will grow dark and cold. Black holes will slowly evaporate through a quantum process called Hawking radiation. Eventually, after an almost incomprehensibly long time, perhaps 100 years or more, even black holes will evaporate completely. What remains will be an incredibly sparse cold universe containing only the most fundamental particles, spread across vast distances, approaching a state of maximum entropy. In this ultimate state, nothing interesting happens anymore. There are no structures, no processes, no changes worth noting. The universe reaches equilibrium, a state where entropy is maximized and nothing drives further change. This is heat death. In such a state, time would still exist in some sense. Space-time would still have temporal structure, but time would lose much of its meaning. With no changes occurring, no processes unfolding, the distinction between one moment and the next becomes trivial. Time continues, but nothing happens in it. This is a kind of end of time, not because time ceases to exist, but because it becomes meaningless. The arrow of time, which depends on entropy increasing and interesting processes occurring, would fade away. Time would exist but be empty, featureless without significance. This scenario assumes dark energy continues to dominate forever. But there are other possibilities, based on different assumptions about dark energy's nature and behavior. One alternative is that dark energy might not be constant. If dark energy increases over time, a scenario called phantom energy, the expansion could accelerate so dramatically that it eventually tears everything apart. Not just galaxies separating, but galaxies themselves ripping apart. Then solar systems, then planets, then molecules, then atoms. This scenario is called the Big Rip. It would occur at a finite time in the future, perhaps tens of billions of years from now. At the moment of the Big Rip, space-time itself might be torn apart. This could represent a true end of time, not just an emptying of time, but its complete cessation. Whether such an event would truly end time or transition to some other state is unclear. It would require physics we don't yet understand. But it's one possible fate suggested by certain models of dark energy. Another possibility is that dark energy could decrease or even reverse over time. If it reverses strongly enough, the universe's expansion could stop and turn into contraction. The universe would begin collapsing back on itself in a big crunch. In this scenario, galaxies would start moving toward each other. Eventually they would merge. The universe would grow denser and hotter. Ultimately, everything would collapse back into an incredibly dense, hot state similar to the Big Bang, but in reverse. What happens at the end of this collapse? Does time simply end in a final singularity? Or could the universe bounce, beginning a new expansion phase? Some theories propose a cyclic universe that oscillates between big bangs and big crunches, forever. In a cyclic universe, time might have no beginning or end in the ultimate sense. Each cycle has its own beginning and end, but the cycles continue infinitely. Time would be eternal, though divided into distinct cosmic epochs. These scenarios, heat death, big rip, big crunch, cyclic universe, are all speculative. They represent different possibilities based on different assumptions about physics we don't fully understand. Current evidence points most strongly toward heat death, but that could change as we learn more. There are even more exotic possibilities. Some quantum theories of gravity suggest that time itself might be emergent, not fundamental, but arising from something more basic. If time is emergent, it might emerge differently in different contexts, or might cease to emerge under extreme conditions. In such theories, asking whether time ends might be asking the wrong question. Time might not be the kind of thing that can begin or end because it's not fundamental. It's a useful description at certain scales and conditions, but breaks down or becomes inapplicable in extreme situations. Another consideration involves the multiverse idea we mentioned earlier. If our universe is one of many in a larger multiverse, the fate of our universe might not be the fate of time in general. Time might continue in the broader multiverse, even if it ends or becomes meaningless in our particular universe. In eternal inflation theories, for example, different regions of the multiverse are constantly undergoing big bangs. While some regions, like ours, expand and cool and eventually die, new regions are always being born. From the perspective of the multiverse as a whole, time might be eternal, with no beginning or end. These ideas are highly speculative and difficult or impossible to test, but they represent serious theoretical possibilities emerging from modern physics and cosmology. There's also a philosophical question about what it would mean for time to end. If time is the dimension in which change occurs, can time itself change? Can it end? The concept seems paradoxical. An ending is itself a temporal event, something that happens at a time. How can time have a temporal event that marks its end? Perhaps the answer is that time doesn't end in the sense of a moment when it stops. Rather, time might become inapplicable or meaningless under certain conditions, just as asking what's north of the North Pole doesn't make sense because the concept of north breaks down at that point. Asking what time is it after time ends might be a question that doesn't make sense. For our everyday lives, these cosmic speculations about time's end might seem remote and irrelevant. The end of time, if it occurs, is trillions of years away. It has no bearing on our daily experience or immediate concerns, yet there's value in contemplating these ultimate questions. They remind us of our place in the cosmos. We exist in a thin slice of time between the Big Bang and whatever ultimate fate awaits. We're temporary patterns of complexity in a universe that began simple and hot and will likely end simple and cold. This perspective can be sobering. Everything we build, everything we care about, everything humanity will ever accomplish, all of it will eventually be erased. The universe has no memory. In the ultimate state of heat death, there will be no record that we ever existed, no trace of our civilization, no legacy of our lives. Some find this thought depressing. If nothing lasts, if everything ends, does anything matter? But others find it liberating or even beautiful, precisely because our time is limited, precisely because nothing lasts forever. Each moment becomes precious. The temporary nature of existence gives it poignancy and meaning. From a Buddhist perspective, impermanence is not something to lament, but to accept and even celebrate. Everything arises and passes away. This includes not just individual lives, but entire universes. The cosmic scale of impermanence doesn't diminish the significance of our fleeting existence. It contextualizes it, frames it, helps us understand our place. Moreover, the end of time, if it occurs, is so far in the future that it's almost abstract. Between now and then, stretch trillions of years of potential history. Countless civilizations could rise and fall. Unimaginable wonders and discoveries await. The story of intelligence and consciousness in the universe is still in its earliest chapters. Perhaps life and intelligence will find ways to persist, even as the universe grows cold and sparse. Perhaps consciousness will spread across the cosmos, finding ways to extract energy and meaning from ever more meager resources. Perhaps we'll discover that the rules we think govern the universe's fate are incomplete, and new physics will reveal new possibilities. Or perhaps not. Perhaps the universe's fate is sealed, and all complexity, all life, all thought will eventually cease. Either way, here and now we exist. Consciousness has arisen in the universe. For this brief cosmic moment, matter has organized itself to reflect on its own existence, to ponder time, to create meaning. As you rest here in this present moment, you're part of that vast unfolding. You exist roughly 13.8 billion years after time began, and perhaps trillions of years before it ends or becomes meaningless. You're somewhere in the middle of time's story, if time has a middle. This moment, this now, is your time. However long or short time's ultimate span might be, this moment is yours to experience. The past has brought you here. The future remains open, full of possibility. And between them, you exist in the ever-present now, conscious and aware, thinking about time itself. The end of time, like its beginning, remains partly mysterious. We can theorize and speculate, but we don't know with certainty what will ultimately happen. Perhaps future civilizations will know more. Perhaps the answer will forever remain beyond our reach. Either way, the question itself reveals how far human understanding has come and how much further it might yet go. We've journeyed through many aspects of time, its measurement, its nature, its beginning and possible end. We've explored time in physics, in consciousness, in memory and perception. Now, as we come to the close of our exploration, let's reflect on what it means to live in time. To be a temporal being, to exist in this mysterious dimension we've been contemplating together. Living in time is the most fundamental aspect of human existence. Everything about your life is temporal. You were born at a particular time, you will die at some future time. Between these boundaries you live, experiencing moments, making choices, forming relationships, pursuing goals. All of this happens in time. Time is not just the setting for your life. It's woven into the fabric of who you are. Your identity is temporal. You're not a static thing, but a process unfolding through time. The person you were 10 years ago is both you and not you. You've changed, grown, learned. You're the same person in one sense, yet different in another. This paradox of identity through change is fundamentally temporal. Your body is constantly renewing itself. Cells die and are replaced. Molecules are exchanged with the environment. The physical matter that makes up your body today is largely different from the matter that made it up years ago. And yet, you remain you. Continuity in time creates identity despite physical change. Memory binds your temporal self together. Your memories create a narrative, a story of your life stretching from past to present. This narrative gives you a sense of continuous identity. You remember being younger, and that remembered past connects to your present, creating a coherent self across time. But memory is not perfect, as we've explored. Memories fade, distort, sometimes disappear entirely. Parts of your past become hazy or lost. In a sense, parts of who you were cease to exist when they're forgotten. The you that exists now is built partly from what you remember and partly from what you've forgotten. This raises interesting questions about identity and time. If you lost all your memories, would you still be you? What makes you continuous across time if your matter changes and your memories are imperfect? These questions have puzzled philosophers for centuries. Perhaps what makes you you is not any particular content, not specific memories or molecules, but the ongoing process itself. You are the river, not the water, the pattern that persists through change, the story being told, even if some chapters are forgotten or revised. This process of being you unfolds in the present moment. Right now is always where you exist. The past is gone, the future not yet here. Yet the present is also fleeting, vanishing into the past the moment it arrives. You live at the boundary between past and future, in this ever-moving, ever-present now. How you relate to this temporal existence profoundly affects your experience of life. Some people live constantly focused on the future, planning, striving, working toward distant goals. Their present moment is sacrificed for future rewards. They're always becoming, never being. Others dwell in the past, in memories, regrets, nostalgia for what was. They're living backward, unable to fully engage with the present because they're caught in what has already happened. They carry the past like a weight, unable to set it down. Both of these orientations miss something essential about living in time. The future hasn't happened yet. It's important to plan and prepare, but you can't live there. The past has already happened. It's important to learn from it and treasure good memories, but you can't return there. The only place you can actually live is now. This doesn't mean ignoring past and future. It means balancing temporal awareness, drawing on the past without being imprisoned by it, preparing for the future without being absent from the present. Living in time skillfully means engaging with all three temporal directions appropriately. Many wisdom traditions emphasize presence, being fully in the current moment. This is the heart of mindfulness practice. Instead of having your attention scattered across time, ruminating about the past, worrying about the future, you gather your attention into the present. You experience what's actually happening now. This is harder than it sounds. The mind naturally wanders through time. You might be physically here, but mentally you're somewhere else, remembering yesterday, planning tomorrow, replaying conversations, rehearsing futures. This time wandering is normal, but it also means you're often not fully present for your own life. When you're present, time can feel different. It's not that time slows down exactly, but your experience becomes richer, more textured. You notice more. You're more fully here. The present moment, when you're actually in it, has a spaciousness that time wandering collapses. There's a paradox here. The present moment is the only time you ever experience. You've never experienced anything except now. And yet you're often not present to your own experience. You're thinking about other times instead of attending to this time. Living well in time might mean learning to be present more often. Not always. Memory and planning are valuable, but more often than most of us naturally tend to be. Present enough to actually experience your life as you live it, rather than always being mentally elsewhere. Time also brings change, and learning to live with change is essential to living well in time. Everything changes. Relationships begin and end. Youth gives way to age. What you have, you eventually lose. This impermanence can be difficult, even painful. Some respond to impermanence by trying to hold on, to preserve, to stop change. But this is futile. Time continues. Change happens. Trying to prevent it creates suffering. It's like trying to keep a river from flowing. You'll exhaust yourself and fail. A wiser approach is acceptance. Yes, everything changes. Yes, nothing lasts forever. These aren't problems to solve, but features of reality to accept. Impermanence is not a flaw in how things are. It's how things are. Moreover, impermanence makes beauty and meaning possible. If moments lasted forever, they would lose their preciousness. If relationships never ended, we might take them for granted. If we didn't age and die, would our lives have the same urgency and significance? Finitude gives weight to time. Impermanence makes moments matter. Your time is limited. This is both sobering and motivating. You have only so many days, so many hours. How will you spend them? What will you do with your brief span of existence? These questions gain importance from the fact that time runs out. Different cultures and traditions have different wisdom about living in time. Some emphasize making the most of every moment. Seize the day. Don't waste time. Live fully and intensely. This orientation values productivity, achievement, experience accumulation. Others emphasize acceptance and patience. Time will bring what it brings. Don't rush. Don't force. Allow life to unfold at its own pace. This orientation values being overdoing, presence over productivity. Both perspectives capture something true. Time is precious and shouldn't be wasted on what doesn't matter. And time will pass whether you rush or not. So there's wisdom in moving through it with ease rather than constant urgency. Perhaps the balance is to be intentional without being driven. To value your time without being enslaved to productivity. To engage fully with life without desperate grasping. To plan and work toward goals while also making space for rest, for spontaneity, for simply being. Time also connects you to others. You share time with people. Relationships are temporal. You meet someone at one time, grow close over time, perhaps part ways in time. The time you spend with others is, in a real sense, giving them your life. Hours spent together are hours of your finite existence shared. This makes time with loved ones precious. Those hours are gone once they pass. You can't get them back. You can't replay them except in memory. Being present with people, really present, not distracted or mentally elsewhere, is one of the most valuable gifts you can give. Time also brings loss. People you love will die, or you'll be separated by distance or circumstance. Relationships that once filled your days fade into memory. This is painful, but it's also universal. Everyone who lives in time experiences loss. It's part of the cost of loving, of connecting, of being embedded in a temporal world. Yet these losses don't erase what was. The time you shared with someone remains real, part of your history. Memory preserves it, imperfectly but truly. And the fact that relationships end doesn't diminish their meaning. Perhaps it enhances it. The temporary nature of connection makes it more precious, not less. As you age, your relationship with time changes. In youth, time feels abundant. The future stretches out seemingly forever. You have time to try things, make mistakes, start over. There's little urgency. In middle age, you begin to feel time's finitude more acutely. You realize you won't do everything you once imagined. Choices have consequences. Paths not taken close off. Time is no longer infinite. You start to feel its pressure. In old age, if you reach it, time becomes both more limited and more precious. The future is shorter, the past is longer. You have less time ahead but more experience behind. For many, this brings a shift in perspective. Less striving, more acceptance. Less future focus, more presence. Each stage of life has its own temporal wisdom. Youth's expansive sense of possibility. Middle age's productive engagement with time. Old age's acceptance and presence. All are valuable. All are part of living a full human life in time. Throughout your life, you're making choices about how to spend your time. What to do, what to leave undone, what to prioritize, what to set aside. These choices accumulate into the shape of your life. You become what you do repeatedly. Your habits, your practices, your patterns, these determine how your time is spent and therefore who you become. This means that how you use time is, in a deep sense, how you create yourself. Each moment is an opportunity. Not every moment is equally important. We can't be intense and intentional every second, but the overall pattern matters. How you spend your days is how you spend your life. Time also gives you the opportunity for growth and change. You're not fixed. You can learn, develop, transform. The person you are now doesn't have to be the person you'll be. Time allows for becoming, for evolution, for the development of new capacities and understanding. This is hopeful. Mistakes aren't final. You can change course, you can grow from difficulty, you can become wiser, kinder, more capable. Time is the medium in which this transformation happens. But transformation requires time. Change doesn't happen instantly. Growth is a process that unfolds gradually. Patience is necessary. Patience with yourself, with the pace of change, with how long things take. Time moves at its own speed. You can work with it, but not rush it beyond certain limits. As our exploration comes to a close, perhaps the deepest wisdom about living in time is simple. Be here now. Not always, not obsessively, but more often. Actually inhabit your life. Experience your moments. Be present to what is. The past is important but gone. The future is important but unknown. The present is where you actually exist. This moment right now is your life. Not a preparation for life. Not a memory of life. This is it. This is where you are. This is when you are. And this moment, like all moments, will pass. Soon it will be past. Another moment will arrive to replace it. This is time's fundamental nature, its flowing, changing, impermanent character. Fighting this creates suffering. Accepting it creates peace. You are a temporal being in a temporal world. You exist in time, are shaped by time, experience time from the inside. Time gives structure to your existence. It makes your life possible. It's the dimension in which your story unfolds. What is time, really? After all our exploration, perhaps we can say this. Time is the dimension of change, the structure of becoming, the medium of existence. It's both physical, a real feature of the universe described by physics, and experiential, something we feel and live and struggle with. Time is mysterious, profound, essential. It's woven into everything, including into your very being. You don't just exist in time. You are temporal. Time is part of what you are. And right now, in this present moment, you are here, alive, conscious, aware of time, thinking about time, existing in time. This moment is yours. It's the gift that time gives you, the ever-present now, the only time that ever truly is. May you spend your time well. May you be present for your life. May you embrace time's impermanence without fear. May you live fully in this temporal existence, making meaning from the finite span you have. Time flows on, carrying you with it. But you're not just passive cargo. You're an active participant, making choices, creating meaning, living your life moment by moment through time. Thank you for spending this time with me, exploring these questions together. May your journey through time be rich, meaningful, and as present as possible. The exploration of time never truly ends. Each moment is new territory, a fresh opportunity to experience what it means to be a being in time.